My name is Atika Pasha. I'm a senior monitoring and evaluation specialist at C4ED. I have been working for over 10 years in the field of evaluation and impact evaluation specifically, or dabbling a bit in monitoring and evaluation as well. Okay, good. Now it works. So as already mentioned by several people, we will start with a recap. You must have already seen the agenda. So we're starting off with just briefly talking about what was discussed in the last 2 years, or well, last year specifically, sorry, which was talking briefly from the CIE methods or counterfactual impact evaluation methods, and then moving on to data collection where Ellie will jump in and briefly introduce himself beforehand. Right, so moving to just a small disclaimer, naturally, this is material that's entirely prepared by C4ED. So, these do not necessarily reflect the views of the European Union here. Okay, brief rules on how we can move forward with the presentation. It's a nice set of people, or a decent size of the presentation group here. But if you are joining in or leaving the call and then joining in again, please remember always to mute yourself when you're in the call. Sometimes there is a lot of background noise, and that can interrupt the flow of the presentation in general. Also, overall, can interrupt the flow of a discussion. Which is where most often the mute button is not on. Otherwise, questions. I am more than happy to also take clarification questions during the presentation itself. So if some concept is absolutely unclear, then I'm happy to take some questions there. I'll try to keep track of the questions in the chat. But regardless, but overall, just the discussion, let's leave it towards the end of the presentation or for the specific sessions designed for that, because I'm hoping to cover all the relevant material with a decent amount of detail. If you have questions, please post, and I'm still talking, or you think it might be relevant to consider this, please post them in the chat room. If any of you find this question as relevant, please click on it or like it so that we are aware that this is something particularly relevant. And if it's extremely relevant and it's breaking, of course, the flow, then potentially Carolyn will also or will inform me, or that I have to sort of break and read out the questions and respond to the questions. And of course, we will use the longer breaks to ask all of the questions, as I already previously mentioned. And finally, for the feedback, again, we are happy to have your suggestions, your comments, and there is a session defined particularly for this at the end of the day as well. So please feel free to let us know what we can change in the slides or in terms of the material that would improve your understanding of the training, from the training itself. Right. So moving on to the agenda for today, we've already covered the first welcome and introduction. We now are already into the session 1, which, as I already mentioned, will recap the CIE methods from year 1, and Ellie will delve into Ellie Plim at CS Dormer will delve into the data collection for CIE for year 2. We will then have a short break around 10 minutes at 11:15. This is Central European time, naturally. 11:25, we will move into the session 2, which would again break somewhere around 12:10 before we conclude at 12:35. Starting at 12:20. And then there is the quiz, which I hope everyone's excited for. Thereafter, lunch break from 1 to 2 p.m. Central European time. And thereafter the session 3, a small break again, and then we will walk through an example of a t-test, one of the methods we will discuss during the session today before closing, before the Q&A session and the closing off. So basically we will have the last 25 minutes of the day for question and answers, as well as closing the session and getting your feedback. So please be aware of this in case you have some very interesting question and we do not manage to cover it during the session itself. Good. So just as I said, we will be talking about counterfactual impact evaluation. So the term CIE is going to be thrown around a lot just in this particular session. And specifically, what we're talking about CIE, we'll be discussing 3 specific methods of identifying impacts before we talk about the data that is required for CIE, or counterfactual impact evaluation. And thereafter, we're talking about basic descriptive statistics. I'm sure that most of the individuals here have had something to do with basic descriptive statistics before we delve into the topic of statistical testing, which is left for the end of the day when you're all very fresh. So let's hope that we make good progress on all of this. Note that we will be sharing all the resources and the case studies on the training at this particular platform that is listed over here, or written over here. Right. I assume there are no questions. Let me just check the chat very quickly. But in any case, the recording has already started, so I believe we're fine on that front. And yes, exactly. So no questions. Okay. So the idea of the first session, or the recap in this round, is to understand what counterfactual impact evaluation is, and then review why we need to do it, what it implies and how we do it, or with whom we would need to do it and how we would do it. So the first step would be to talk about one of the most standard methods in counterfactual impact evaluation, which is randomized controlled trials. If anyone has a medical background, they are well aware that this is a very standard method used for testing in medicine, and then was brought over also to several other fields, including economics. And this is what we will briefly discuss, and the intuition behind it as to why randomized control trials in this field of counterfactual impact evaluation is the golden standard of methods. And then we will, as I mentioned, briefly review 2 methods, which is matching and difference, some of which would be, or a lot of it will be relevant for you, given that your own projects might have this as an evaluation method. Okay, so why do we do a impact evaluation, counterfactual impact evaluation? And in this case, again, most of you are aware of monitoring and evaluation, where you are looking at an impact. So you are estimating your outcomes at the start of the program till the end of the program. How counterfactual impact evaluation differs from a monitoring and evaluation, or process or evaluation in this way, is that it specifically defines that the change that you observe in your outcomes is causal or attributable to the program itself. And then the key feature is that there are methods that might potentially explain the mechanisms, but in this case, not only do we explain the mechanisms, but we're able to define the magnitude, or quantify what part of the effect that you observe is due to the program that you are actually implementing. It's also important it's becoming more and more important to test what works best. So there are many ways you can run a program, many components that you can work with out there, and it's important to learn which strategy works best. And this is where a counterfactual impact evaluation is extremely useful and quite robust in giving you a response to which method might lead to more employment or more income in 6 months, for instance. And then naturally, based on the results from your impact evaluation, you're able to make evidence-based decisions or know what works, how, and to what magnitude. Right, so I believe everybody here is aware of the word evaluation, so I will explain the other two words, which is impact and counterfactual. So also everybody, I assume, is aware of the word impact. It's defined differently across many of the resources I came across. However, the definition in a CIE is that it is basically not only establishing an effect for your outcome of interest, let's say we're talking about employment, and what the effect of your program or policy was on employment, but we are assuming something called causality and attribution. So these are the two keywords that are associated with CIE or impact within CIE, that we are sure that the impact that we are measuring is caused as a result of the program, is directly attributable to the program. And then to establish that, we need a counterfactual. And the idea of, or we need to simulate a counterfactual, or the idea exists that we would like to know what happens if the program had not been given to the participants, how their employment would have looked like in a year. And if that was to be the case, we would be able to assess, okay, they are currently 50% of the population is employed or in some form of employment, whereas had they not received the program, it's only 30%. So we know that we've made an improvement of 20 percentage points. So basically, the idea is we need to understand or get to know or have observed the program beneficiaries had they not received the program. Naturally, you see a fundamental problem here, which is it's impossible to measure and observe the counterfactual. If you've given a program to someone, then it implies that they cannot not receive it. So you cannot observe the same individual in both scenarios at the same time. And that's why the entire premise of a counterfactual impact evaluation is to define or mimic a counterfactual through the creation of a control or a comparison group. So how do we design it? Again, as I said, we need to now create our counterfactual situation, and we need to create our comparison group or mimic the counterfactual through the creation of a comparison group. And of course, if we are now creating a group to compare our beneficiaries to, we have to make sure that one group is not a set of apples and another group is not a set of oranges. We need to be able to compare red apples with as red as possible apples. And this is basically the main premise of a comparison group. You need to have, on average, the same type of characteristics in your control group or group of individuals who have not received the program as your treatment group. And again, this brings me to the second point, they should not have received the program. If you're basically treating, if you're considering individuals who've also been somehow affected by your program, then you're basically comparing someone, then you're not creating your counterfactual situation. And then finally, what we're expecting from the control group is not that they react completely differently to the same treatment or the same program, but that they have a similar reaction or a similar trend in terms of employment or income, for instance. So just again, coming back to the apples example, if I was to give fertilizer to an apple tree and if I was to give fertilizer to an orange tree, the differences would be very different. However, what one would expect is that if you give the same fertilizer to an apple tree and another apple tree, they would react in a similar manner. And so this is effectively our comparison group that we are trying to create and is central to any counterfactual impact evaluation of CIE. Naturally, it's not the case that we can design a counterfactual the same way everywhere. There are differences in programs. There are differences in contexts. You might have a humanitarian setting. You might have COVID was one of the settings. There's timeline as an issue. Some programs run for a year, some run for 5, some run for 10. And then, of course, the data availability and the budget that is associated with your program and the evaluation of the program. And so we will specifically suggest, or we can design several types of counterfactual CIE methods, or we have several CIE methods that can be modified to fit to several contexts. And it's basically relying on your creativity to understand, and your understanding of the program naturally, to define your method most suitable for your program. So to talk about how many of you might already be aware of how a counterfactual works. So here we have about 2,000 youths who are being selected for a youth vocational training program. The idea is that these they look few, but there are 2,000 individuals, let's say 1,000 males and 1,000 females, who have now applied. And after their application has come through, they are called in for an interview. Now, based on this interview and their application, they would either be defined as people who will be selected into the training program. Very often you will hear the word treated or treatment, and that's basically saying that similar to giving medication. So it's a treatment to the group of individuals who are, in this case, going to be trained or are going to enter the training program. And as opposed to them, we have the other 1,000 individuals who were not selected for the training program. And this might be this might be a question, or this might be a area where I stop or where we can stop and ask ourselves, is this a good counterfactual? The group of individuals who was rejected for the training program based on their application and their interview, are these going to be comparable and similar to the group of individuals that were selected for the program through the interview and application? The simple answer is not really. The idea is that if you have chosen, so there are always in programs, and again, I don't have to explain how programs work or how selection program works to everyone here. The idea is that you choose a particular set of applicants very often, or you target certain criteria, or you have certain criteria to target these applicants. So they can be stronger, or alternatively, you're looking at a more vulnerable population, so they can be weaker in general. So amongst the people you've rejected might be the people who are more well off, have had previous employment experience, and so on. So these youths could be left out. However, for the sake of this example, we are saying that we're more interested in youth that did a better interview, that were stronger applicants in general. And they were the ones, 1,000 individuals or youths that were chosen. And so what we see is that they are a stronger set of applicants who are not comparable to the weaker set of applicants. They have probably better academic qualifications, stronger communication skills, are able to perform better in an interview. And these are the factors that have affected not only their selection into the program, but also their selection eventually into, or their performance after the program. So while this is most desirable for having these kind of applicants into the program, it's not necessarily desirable for a CIE method. That is because, again, the groups are not easily comparable. And so given the selection process, again, we would want to understand why or how these differences can be relevant for an impact evaluation. So just to give you very brief examples, our eventual goal is that these trained youths are better able to find employment, so they will be employed after the end of the program, and they will have a better and more higher incomes and maybe a stable source of income, right? And so knowing this, let's just compare the two sets of individuals that we have selected or not selected into the training program. So what we would see, again, considering that we are interested in more stronger candidates or have selected more stronger candidates into the training, is that on average, these are individuals or youths who are slightly older, so on average 30 years of age, they have more years of schooling, they have had previous employment, and potentially come from a wealthier background as shown by their parent income. Opposed to these individuals or this group, we have the group that was not selected, and that could be a set of individuals who are younger, who have fewer years of schooling, who are so therefore less qualified in general, have fewer experience or less experience with employment opportunities, and who are not necessarily coming from a very good economic background or at all a well-off economic background. And this is basically creating systematic and visible differences between the two groups. But there is another factor that I also previously mentioned that we cannot account for. So even if we are able to control for these observable differences or account for these differences between the two participants, there's still the difference that comes from unobservable characteristics. So while both might be equally motivated, we cannot be certain that they're both having the same level of confidence or the same level of determination. And what this implies is that even not just in observable characteristics, but also in unobservable characteristics, these groups are different and will therefore perform differently, thereby affecting their eventual outcomes in employment and in terms of income that they have at the end of the program. Right. So, as we said in the previous example, we cannot just take the set of rejected applicants and consider that as a counterfactual. Again, the idea being that we need to have a comparison for what happened had the program not taken place. So we need a similar set of individuals to be considered as a counterfactual group in our case. And how would we now go about designing or setting up our counterfactual group in this case, and we were to not take the rejected applicants? And this is where we talk about the randomized control trial, which is, as I said, again, one of the gold standard in terms of impact evaluation methods. Right. So if now the evaluation is supposedly integrated into the program implementation, so now before the program is starting, you bring in your evaluation experts, or you yourself step in and decide that you want to do a randomized control trial. What are the benefits and how would this be done? The simplest way that we are talking about is something called a lottery design. Let's say all 2,000 applicants are put in a row, and every second individual would be told, you're receiving the program. Second, fourth, sixth. So everyone who's an even number will be told they'll be receiving a program. Everyone who is an odd number will be told they are not receiving a program. So we've randomly, or let's say through lottery, decided who will be selected and who will not be selected into the program. Now, how does this help, or how does this random assignment of individuals into the treatment or into the program versus into the control or not receiving the program help? And here, the basic idea is that if, or the basic idea relies on the principle called the law of large numbers. And the law of large numbers simply says that if your pool of applicants is large enough, if you were to randomly assign the two groups, they are on average similar. And so you will observe in a large enough group of individuals having randomly assigned that that they will end up looking more similar than individuals who are than not through a non-random process. And this basically implies that having taken our group and now through the lottery design, again, just standing them in the row saying all even numbered individuals will be selected into the program and all odd numbered individuals will not be selected in the program, will bring into action the law of large numbers and ensure that the characteristics observable, for instance, will look much more similar between the two groups. Again, they won't be the same, but they would be very similar. So again, the ages will now come to closer to each other, will be, let's say, on average 27 years. They will all have about 8 years of schooling, similar experiences in terms of employment, previous employment, and then in terms of parental income, also similar. So they are coming from similar backgrounds or similar observable characteristics. What one also can be a little confident about in this case, or through the law of large numbers, is that the unobservable characteristics between these two groups are also similar. So they are similarly motivated, they have a similar amount of confidence, self-confidence, and a similar amount of determination to succeed at the end of the program. And this basically is how you've created a counterfactual group that is comparable through to your treatment group or the youths that have been selected into the program. Are there any questions? Okay. Then let's just talk very briefly about how randomized assignment creates these groups, or how we would measure this. So just briefly looking at this graph. Now on the x-axis, we're just measuring years. So in 2019, let's say the program implementation begins and is expected to end in 2023. All years before the program are the pre-program phase. This is the program phase, and this is the post-program phase. This now is the y-axis. We are just measuring the income of each of the individuals, or let's say the groups that we have in our data. Again, if you remember from the example, we started off, every one of the individuals who we had randomly assigned started off with about 4,300 as their parents, or let's say they started off as 4,300 as their income level. Because these two groups started off similarly, through the impact evaluation, let's say the program implies that those who were selected into the program end up with about 5,000 units as their level of income in 2023. And those who were not selected are also having a higher income, but not necessarily the same as the individuals who were selected into the program. And this basically is what we consider as the impact. Between those who were not selected and those who were selected, we see that we have a difference of 600 units. So basically subtracting 4,400 from 5,000. What you can also see from this graph is sort of the intuition behind an RCT again, or just a CIE in general. If we did not have the counterfactual group, so those who were not selected, what you usually would be measuring is 4,300 as opposed to 5,000, and telling us that your impact is 700 units, which is not the case, because as you see, through whatever reasons, the not selected group was also able to perform better and improve their income to 4,400, and therefore the impact actually of the program is only 600 additional units, whatever units you want to consider in this case. And therefore, the intuition of creating a counterfactual is hopefully sort of visible through this simple graph or example. Right, what again brings us, or what I want to bring us again to, is now the two words that I stressed previously. One is causality and second is attribution. Now, through this random assignment of individuals into the treated, control, or into the training program versus not, we can be certain that they were on average comparable at the beginning of the program. And therefore, the impact that we observe at the end of the program, so this 600 units increase in income, is clearly as a result of the program itself, because all of the characteristics that we observe in the group were similar. So it's only the program that led to a change in their income. Right, so what to randomize? So far, we've looked at the case of individuals, so 2,000 individuals who are randomized, but note that there are other aspects of a program that the implementation can also randomize, with a key qualification here being that you need to have full control over the implementation of this program. So as an evaluation team, you try not to go for aspects of your program that are, let's say, affected by the weather. So whether a treated group will eventually be affected by climate change, or whether the treated group will be affected through war differentially or through migration differentially. So these external factors should basically be similar across both, or you should have a program section that is completely sort of controlled by you. So who gets the training when, who gets an incentive when, who gets subsidies when, and these aspects are all under your control, and therefore you can not only rely on individuals, but you could, for example, also randomize firms who receive, let's say, a financial backing, or you may also randomize trainers who will receive incentives to do their training versus not. And these are the kind of aspects that you can randomize. It often requires creativity, as I already previously mentioned, and a thorough knowledge of what your program is about, what you can control, and what external factors can come and impact the randomization. And so it's important to think of those factors and to plan well ahead. When to randomize? Again, this is one key message that comes from that must come through for any RCT. Randomization has to take place before the program starts. After the program starts, you have not been able to randomly assign your individuals, and therefore the creation of counterfactual has been compromised. And then finally, how to randomize. We talked about the simple lottery design, or standing everyone into a row and considering all the even number individuals as treated, or as the group that will be receiving training. We could also consider multiple treatment arms. So let's say your program does not just include training, but also provides implements to individuals who have been trained, let's say a sewing machine. And in that case, you can not only just say, you can say that every second individual would receive training, but every third individual would receive a training and an implement on top. And these are sort of different treatment modalities that you can test also using a randomization, again, through a simple lottery design. And there's a phase-in design. Again, this is sort of in cases also where you know that you have a limited number of individuals and you would have to treat everyone. However, you've run out of resources in order to treat everyone at the same time. So what you do is you stagger the rollout of your program. And through the staggered process, you randomly decide who gets it in the first year versus who gets it in the fourth year. And therefore, through this randomized assignment, you know that your fourth year group can be considered your control group, whereas your first year group can be considered your treatment group, to establish the impact of the program across 3 years. And then finally, we have the encouragement design, where if you are unable to if you're able to provide treatment to everyone and would like to do it because of whatever reasons, you can change, you can give access to everyone get access to the program to everyone, but in this case, actively encourage some to participate, let's say through flyers, through an information campaign, through other methods, versus through radio jingles, whatever other awareness or nudges that you can think of, versus some who are not given these nudges but still have access to the program. And this is the encouragement design. We're also aware, however, that there are cases where randomization is not possible. It's not socially or politically acceptable. You are intending to target more vulnerable sections of the population rather than randomly assigning it to everyone. You consider it's just not feasible. Again, let's say the program has already started and now randomization cannot take place. And then these are and then in this case, we need to rely on other methods that, for example, would allow us to still develop a counterfactual evaluation inside your program. And this is where we are talking about quasi-experimental or half-experimental methods or partly experimental methods. So quasi-experiment methods are additional techniques that have been developed to construct your counterfactual. And again, the idea is that it tries to, in this case, mimic what is happening in a RCT or in a randomized controlled trial. And again, because this again shows you that because you're trying to mimic what's happening in RCT, the idea is that the RCT is still what we consider as the gold standard, but we can try to mimic it using other methods. And specifically, we're talking about two methods, which is matching and difference and differences. Right, so for matching, the first example, again, let's say we are targeting a certain group of individuals. So those who are selected in the program are, again, looking different than those who are not selected into the program. What one would do in terms of matching is take these two groups, and then through a technique called matching, what one would do is simply look for pairs of people that are similar in terms of characteristics. On average, you would try to ensure that the group of individuals that you're matching are similar in, let's say, gender, similar in employment status, similar in wealth status, well-being, etc. And these are the factors that eventually should ensure that even though you have not been able to randomize, you have been able to create two groups that are more or less similar, even within your selected or not selected group. Having done this, you've been able to create now or mimic again a counterfactual situation and thereby create a treatment and comparison group so that you can analyze them and see what the actual impact of the program is. One final key point that is relevant for this is that you must consider pre-programmed characteristics or characteristics that do not change over time. Therefore, you cannot look at individuals 10 months later after the program has started and then look at their income status, but must have information on their income status prior to the start of the program. Right. So having done your matching, you again will hopefully have individuals that look relatively similar. Again, now a smaller set of individuals because everyone in both groups cannot find a comparison. Remember, we looked specifically for people who were better in the treatment group versus the weak candidates who were not selected. So we have to find the sort of better ones in the comparison group and the worst ones in the treatment group to be finding our comparison between the two. Again, this is a little challenging in trying to derive this type of groups. Therefore, it's important that you keep in mind that the larger the first sample you have, the better chances you have of finding comparable individuals between the two samples. Right, and the final change, of course, remember we were talking about observed characteristics and unobserved characteristics, and in this case, it's important to remember that matching is able to only consider observed characteristics, so age, years of schooling, previous employment or years of employment or parental income, but is unable to capture unobserved changes such as, for example, self-confidence or motivation. Right, and then finally, we talk about difference and differences, which is the third method that I mentioned we would be discussing. And this, again, relies on the fact that you can start off with two different sets of individuals. You can do your interviews, you can select the stronger set of individuals into your program. How then can we compare or get the effect of the program? And this is sort of defined through the difference in differences approach. Having understood that two groups are different, we need to figure out what did they look like before the program starts. And initially, between the treatment and comparison group, we observe the first difference, or this being, let's say, the difference in income. So one starts at 4,300 and one starts at 4,000, and therefore is sort of the less well-off group. What we should observe in the two groups is eventually what happens to the treated group after the program and the comparison group after the program. And here you will observe that, let's say, the treated group is doing much better, and now they are earning, let's say, about 6,000, whereas the comparison group is earning about 4,200. And so there is a difference that you consider at the end of the program. This is called the second difference. So remember, the first difference was at the start of the program, and now the second difference exists at the end of the program, which is about 1,800 units of income. In this case, to establish your impact, you would have to subtract the first difference from the second difference. So the initial difference in income has to be subtracted from the first difference in income to generate your impact of the program. So what you can see through this graph is that you need the information of both groups at the start of the program, at the end of the program, and in fact, even if possible, before the program. And now, why do you need all of this information? And this is because the difference in difference approach relies on one main assumption, which is the parallel trends assumption. What this means is that if we were to observe the two groups before the program, let's say the 2 years before the program, and we were to say the average income of both groups, on average, they should be following a similar trend and should, in general, be looking similar or evolving similarly across time. And if we have this assumption, we can assume that had the program not taken place, they would have again continued to evolve similarly over time. And therefore, this is your parallel trend, what would have been the case had the treatment group not received the program. It's just similar or parallel to the comparison group, just adding the first or the difference between the two groups to the current status of the comparison group. And this basically, this assumption is what you exploit to generate your impact in the difference in difference method. Or basically saying that I subtract these differences that I know would have stayed the same across time had the program not come across to the treated group. Right. With that, I think the two or three most commonly used methods of counterfactual impact evaluation have been covered. And this was, again, something that was done previously in year 1 of your training. So those who were in year 1 of training can refer to it. And there were also other experimental, quasi-experimental or partly experimental approaches that were discussed to conduct CIE or CIE methods, which is instrumental variable and regression discontinuity design. We won't go into these, but please refer to year 1 to remember what these were about. And there's also some resources that I provide here in terms of what you can look at. So books, videos, and podcasts that you should listen to understand the concept of counterfactual impact evaluation. And with that, I leave the floor to Ellie.
Thank you very much, Atika. So before I get started, just a brief introduction of myself. My name is Ediplim Atiatome, and I've been working with C4ED for the past 3 years as a research manager. My main role has been in the organization and coordination of data collections across these EUTF projects. And I was part of the presenters for year 2, and that's why I'm here to do just a brief recap of what we discussed during the year 2 trainings. So I'm pleased to be with you. I will just quickly get started. So it's a very brief presentation. Yes, okay. So for year 2, the main topic was on data collection for counterfactual impact evaluation. And I think one of there are 3 key things that we focused on. We tried to review and look at the different aspects of preparing for a data collection, and mainly because we consider data collections as being central to counterfactual impact evaluations. And so we spent some time trying to understand the different components of this process. And then we also did spend a bit of time trying to look at, we tried to look at sampling in general, and then sampling frames, which is an important part of data collection. And then also we tried to look at some of the practical issues that you would be faced with when you are collecting data. And the focus for year 2 was really on the collection of not just, any kind of data, but quality data, which is very critical for counterfactual impact evaluations. And so I will just briefly go over this with you before we get started with today's main sessions on data analysis. So as Attica has already gone through with you, we've talked about the different kinds of methodologies when it comes to counterfactual impact evaluations. In terms of the possibilities that you have, regardless of what methodology you choose, one thing is critical and one thing is central to all of these methodologies, and it's data. It's the role of data. And when you look at data, data will influence your counterfactual impact evaluations in different ways. One way it could influence your counterfactual impact evaluation is your decision as to what methodology to use, because data or the data available will tell you whether you can do a matching or you can do a difference in difference, whether you can do an RCT. This is highly dependent on the data that you have. Also, when you do counterfactual impact evaluation, the whole idea is for you to measure impacts. And for you to measure impact, you need to use the data. And so the data itself is critical to your selection of the methodology, and then also to the impacts that you will measure in the end. And for that matter, that's why we stressed on the fact that quality data is very critical to CIEs, mainly because with quality data, you are able to assure yourself that the conclusions that you get or the impacts that you measure at the end of your impact evaluations are exactly what exists and are not, something that you probably were not out there to measure, right? So quality data was something that we stressed on a lot about, and most of the presentations focused on how we can actually collect quality data for counterfactual impact evaluations. And as you see from the image there, when you put garbage in, garbage out, which means if you put in bad data, you are going to get bad results, which mostly we would refer to as, either underestimating or overestimating your impacts. And this has some effects, or the knock-on effects sometimes you cannot estimate, because you might assume that a program is having an impact. However, it is not having an impact based on the kind of data you've actually collected to measure this impact. And it would mislead you to take wrong decisions as to whether to scale up a project or to downscale it. And so it's really critical that the collection of quality data is taken seriously when you're doing counterfactual impact evaluations. And I think one thing that we stressed on about was the different kinds of data that are available for us in terms of when we're doing counterfactual impact evaluations. There are different kinds of data available for us, and that will also determine on, again, what methodology you could use and how you can use them. We talked about quantitative data and qualitative data, and I think we are all familiar with quantitative and qualitative data. Quantitative mainly being, numbers and statistics, whilst qualitative data refers more to non-numerical data, which kind of helps us to understand better some of the processes behind impacts when we measure them. And we talked about how mixed methods have, kind of helped in understanding not only the impacts with regards to beneficiaries, but also the experiences of implementers and other stakeholders, for you to also understand what processes went on behind stages, such that the impacts that were measured actually came about. And I think mixed methods have become quite beneficiary for us. So even though we stressed or we talked a lot about, quantitative data, we did spend some time to talk about how qualitative data is complementary and also helps us to understand quite a lot about the impacts of projects. And we also stressed on the importance of data by talking about some of the other uses that we could use the data for. And we talked about how, monitoring data in itself is very important for counterfactual impact evaluations. In as much as data is important in performing the impact evaluation itself, doing or collecting data for monitoring purposes is helpful for the project implementers on their own, because it gives you an idea of what you are putting into the project and what you are getting out of it. And it is also very critical for the impact evaluation itself, because you would realize that at the end of the day, we depend a lot on the monitoring data you collect to make decisions as to what methodology to use, or to make decisions with regards to, some of the impacts that we are getting, just for us to have a better understanding of the impacts that we are looking at. So as we did spend some time, because we talked about this importance of data, we indicated that you need to spend also enough time planning your data collections. You will spend some time or a lot of time trying to plan or select your impact evaluation methodology, and you will probably spend an equal amount of time trying to figure out what kind of process you need to go through to collect data that's quality, to help you understand the impacts that you are going to be measuring. And so we talked about how data quality in itself, right, drives us to make sure that data collection in itself is intentional. It shouldn't be an afterthought. So don't plan your impact evaluations without considering the different different problems or the different challenges you could be faced on the field when it comes to the collection of quality data. And so in order for us to get that clear, we stressed on how you should move from planning your data collection right from the word go to the basics, which is looking at your evaluation questions, what you are interested in terms of your objectives, turn these into constructs, and then how you actually break these down into indicators, and how this actually goes down to create the questions and the responses that you are interested in. And I think one example we talked about when it comes to, the concept was to first define the concepts within the evaluation questions. Once you've defined these questions, one thing you should ask yourself is that, how can we measure these concepts, right? How can we measure these concepts in the real world? Of course, there is the theoretical aspects of it, but you need to think about what are the, the practicalities of measuring these concepts that you have actually come up with. And these would help you select your indicators. And then we come down to the questions within the survey. Now, in terms of this, we just provided just a brief example of, how we're trying to look at an intervention impacting on a livelihood in terms of economic well-being. And we stress on, for example, how we could pick employment status as an indicator. And based on that, we can categorize this employment status into the different categories that we have here to determine the economic well-being of people who are benefiting from a particular intervention. So this is a general process that we think that it's very important for you to follow in planning your data collection. This relates to the tool development, but also it does relate to the different ways you would be collecting the data. And so in terms of the data quality itself, we stressed also that tool development is critical in terms of the quality of the data that you collect. And so you need to make sure that the tool in itself is of good quality. And for you to do that, you need to leverage on existing literature and tools. What you don't have to do is reinvent the wheel, but try to go back to basics, read on what the topics or what has already been said about the indicators, and try to get indicators already from there. Once you don't find any, then you can construct one on your own to measure your different indicators. Also, it's really important that you pre-test your tools to make sure that they actually measure what you want to measure. Because if you don't pre-test them, you would end up measuring something which you are not interested in. And so it's really critical that you do that. We also spend some time to talk about some of the factors that could contribute to you designing a poor questionnaire, which includes, for example, having double-barreled questions that have 2 questions in one, for example, or questions that are very difficult for respondents to answer. For example, questions that include arithmetic or mathematics in it. These are difficult for respondents to answer on the spot. And so we stress on how you need to avoid this. And so these things we indicated that are important for tool development. Also, we talked about sampling and how sampling in itself is critical to quality data collection. We did talk about the different definitions for a population being the group that you want to actually make inferences to, and then the sampling frame referring to the different units within the population that you want to study, and then also the sample itself, which is the units that you would pick out of the population to study. So the main reason why you would actually get a sample is because it's always expensive to study the whole population. And so you will want to take you want to take a sample out of the target population to actually do your data collection. And then respondents generally referring to the people that you're collecting data from. Also, we did talk about, and this is what I was referring to, that focusing on the sample is always better. For example, with the EUTF Senegal project, where there are, for example, 4,000 farmers, collecting data on 4,000 farmers is impossible. And so it's always important that you get the total list of the 4,000 farmers and then try to construct your sample out of that. And really, what you would want to look at is people who received the program, and then also try to identify the counterfactual, which is people who did not receive the program, in order for you to get a sample that's representative of the population, right? When you don't do the sampling properly, you would face what you call coverage error, which means that your sample does not look like the population that you have. It doesn't represent it, which means that you don't have people who will be able to give you, a counterfactual, as Attica mentioned earlier on. And so it's really important that you consider this when you are doing your sampling. And also, once the sample is collected, in order to avoid coverage error, you need to make sure that the sample itself is complete, is valid, and reliable. All of these will help you avoid the coverage error. In terms of sampling frame, it's always good that you look at databases, for example, application databases or information on replacements, which is something that we always stress on when we speak with you with regards to how your beneficiary lists are always updated with the most up-to-date information, so that when someone drops out of an intervention, you would know. And this is where monitoring data comes in. So you need to make sure that you keep track of all of these when you are actually collecting data, especially for monitoring purposes, because at the end of the day, it's going to help us do a really good sampling to do our counterfactual impact evaluation. And as I mentioned, in order for you to do that, the monitoring data must be really good. In order for you to do that also, you need to ensure that the quality of the monitoring data in itself is ensured. Because if you don't do that, what would happen is your impact evaluation itself would be threatened. Okay, so, and what sample you draw also is highly dependent on the kind of research questions that you have. All of this would determine what kind of sample that you would want to draw. The whole idea of sampling would be that you would do an unbiased sampling in order for you to get the estimates. And we always stress that a generally bigger sample size will always give you a better estimate. When the sample size is smaller, the likelihood of you finding a good estimate is really low, because once you have a bigger sample, it always shows you, or it gives you a clearer picture of the population. And with that, you are able to actually collect data from the sample that is representative of the population. And there are different types of sampling, probability being the likelihood of someone being part of it is solely due to chance. And then there is the non-random sampling, which is mainly purposive in the sense that we choose people specifically to collect data from, mainly because of they being beneficiaries. And this is used mainly in qualitative methodologies, yeah. And as I mentioned, the sample size is critical. I will not spend too much time to explain this. I think we provided quite a lot of material. You can refer to the slides from last year, but we did discuss issues related to how a bigger sample size will help you get would increase your statistical precision in the sense that based on the statistical test you use, you are most likely to get accurate information that is reflective of the population that you are investigating. So you can refer to the slides in order for you to have an idea of what this refers to. There are some trade-offs, because mainly determining the sample size always is dependent on how much funds you have, right? The more funds you have, the more you are able to increase the sample size. And so there's always that balancing between the sample size and what we refer to as the minimum detectable effects, and then also statistical precision. And so you would always have to try balancing this out in order for you to get a good sample that's representative. So I will just skip through these quickly, so that I'll scan through quickly so that we can have our break because it's already time. But one important thing we stressed on was non-response and how that affects your data quality, because non-response will lead to attrition, which means that you are going to lose data, mainly because you did not plan the data collection well, right? If you don't plan the data collection well, the chances that you will not reach the respondent is really high. And the chances also that you'd have high refusals based on how you have poorly designed the questionnaire can affect the quality of your data, leading mainly because you would have a high non-responsive rate. And also, if the non-response is non-random, right, then it may lead to biasness, which means that it's not going to be representative if the non-response is across the population in the same way. For example, within beneficiaries and non-beneficiaries, if it's the same way, then it's not a problem. But if it's different, that you reach more treatment group than the control group, then it will be a problem for your analysis. And we talked about how you can ensure the quality of your data, mainly by planning your data collection well, right? And as we mentioned, designing a field protocol is really critical to understanding or to actually creating a very good data collection, And that field protocol includes training your field staff and getting them ready for the field, showing them the different parts of the questionnaire that they should be careful of in terms of where they should watch out for. And also monitoring the data that you collect. All of these measures you need to put in place to ensure that your data collection is successful. And we talked about the different possibilities that you could use, including using the different computer-assisted programmed interview softwares. We explained quite into detail what these softwares do and their advantages, just so that you can make a choice as to what to go along with. And we talked about the different ways you could use technology, such as using GIS to determine your sample or to create your sampling frame, and then also for quality checks to check where interviews are going on with enumerators. All of these, we spent quite a bit of time. And then we stressed also on how different monitoring evaluation is. And I think Atika mentioned that already in terms of what is different with monitoring evaluation or what is different with counterfactual impact evaluation. I'll not go into it, but you can refer to our slides and then the videos also from last year's training, and you'd have a full understanding of what this difference is. And lastly, I think when it comes to ethics, we stress that there's no counterfactual impact evaluation that is, worth the risk of your participants. Okay, any counterfactual impact evaluation that puts your participants at risk in any form, it's not worth it. And so you need to really think about it. If you're going to be asking questions that is dangerous to respondents, you need to think about it and restructure it, or put in place different measures that would ensure the protection of your respondents. And this is something that we indicated as really critical, that you get the informed consent of participants or respondents before administering questionnaires to them. And also the importance of obtaining ethical clearance based on the different rules or laws that exist in different areas or jurisdictions. You need to make sure that you apply to the relevant ethics board for ethical clearance before you collect data. And so we stress also on these things. I think data security and protection mainly is one of the issues which, as data collectors, we always have to ensure that we protect the identities of participants. And so we stress also on this. As I mentioned, you can check the slides and then the videos because time is already fast spent. So I think there are some of the links here for the different parts of this presentation, but as we mentioned it again, we'll make the videos available. We'll share the links with you probably during the break, and you can have a look at it in your free time just to have a better understanding and refresh your memory about all that we did for year 2. So I would like to bring that to an end here, and then we go for our break.
Okay, so it was a short break, I'm aware, but let's keep the energy going in the same way for the second session, which is now going to be about descriptive statistics for monitoring and evaluation in general. So in evaluation, including counterfactual impact evaluation. Before I assume I can start, Caroline, is there? Yes. So exactly.
Sorry, Attica. I think I have a little problem with recording.
Okay.
Let me try again, because I did so and then it stopped somehow, but can you record it?
Yeah, it's working for me.
Okay, thank you.
Right? Do you see a recording?
No. Normally I see a red button would say the recording has started, but I don't know.
Check. You are going to check and I'm going to check and show it to you. It is there. Then out of that, you are supposed to have number of copies of illustrated manuals printed out. Now the manuals, the previous manuals to print out. Moses, what are the issues that we are facing now? Yes.
Okay, good reminder, everybody mute yourself, especially if you're in another meeting. But yes, so I hope at least it shows to me that the recording appears to have started, so I would assume that it is continuing. And just start, Caroline.
Okay, yeah.
Okay. Good. So the second session is now about descriptive statistics, and basically when you have your data, what do you start doing with it? So again, now we've sort of talked about the methods for counterfactual impact evaluation. Ellie briefly delved into the practical aspects of data collection, not only for CIE, but also for monitoring. And now the third step is you've designed your evaluation, you've gotten your data, what are you going to do with the data? And this basically is just the first session where we start and go over the basic data analysis concepts that would help you inform and understand how you can exploit your data the most and understand how it can help you in doing your evaluation. Since we are keeping it rather basic, there is no previous knowledge for statistics required. We're trying to explain it as intuitively as possible. However, if this is not the case, you know, and you have previous experience in statistics, that is even better. Again, if there is some wording or some clarification that is needed during the slides, which would impede your understanding the further slides, please feel free to raise your hand or write your question in the chat. And I will try to keep track of that. So, as I said, the first, this session, session 2, is about descriptive statistics. Session 3 will be about statistical testing, and tomorrow we will delve into regression analysis. There is also the qualitative data and qualitative analysis that Erik Bliem already talked about, but that will also be covered tomorrow. However, my main sessions in terms of quantitative data collection analysis would be these specific 3 concepts. And specifically for this session, we are looking at descriptive statistics. So the whole session will be to try to understand what kind of data there is out there. So categorical continuous data, how we go about tabulating it, or visualizing this data or elaborating on this data. We talk about measures of central tendency. There are 3 measures, mean, median, and mode. We rather focus on mean and median, not so much on mode. Again, these being the most commonly used methods in evaluation. Then we talk about the dispersion in your data, or how widespread your data is, and the measures that you can use to capture this dispersion. And then briefly go into outliers, which is basically these entries or these cases or observations that are particularly different compared to the remaining observations. Right, so what are descriptive statistics? You would notice this is more a terminology used very often by economists when they say, okay, we need some descriptive statistics. All the papers will include descriptive statistics, or in social sciences, the common terminology, and it basically implies an overview or a summary of all of the quantitative information that you have in your data set. These are basically statistics that can help you understand the key characteristics of the program. Who are you dealing with? It can, for example, also help you confirm whether your program goals are being met. Again, when you collect your monitoring data, you assess you generate your key performance indicators, again, indicators that tell you whether your program goals are being met across the various years of the program. And then finally, you have the possibility, with the help of these statistics, to understand what unusual patterns you observe in the data, or what problematic patterns you observe within your program population, for instance. So just talking about the types of data we have, there are the first type of data is categorical data. I'm not sure how many of you are aware or have heard of this terminology. And the categorical data basically just talks about categorizing individuals, or let's say firms, or whatever your unit of observation is, into a category. So these are exclusive categories, and it implies that you can have one of 2 or one of several values. So when we talk about one of 2 values, we're talking about something like gender. Are you male or are you female? And that is a category which you've allocated to individuals. And in this case, in this particular case, we are considering it a binary variable, or having 2 values. So a dichotomous outcome. So several ways to say the same thing. Effectively, categories or gender is a bi-categorical variable, or information that you have on your individual. There's also something that can exceed or categorical variables can also exceed from 2 categories only. For example, employment status. You might be part-time employed, you might be fully employed, you might be self-employed, these are all categories in which you can categorize individuals. And this is then again something which you would call a multiple or several categories, or not just a dichotomous variable, but a categorical variable with several values. Again, several single categories and mostly exclusive categories, not just mostly, sorry, definitely exclusive categories. Again, employment status can be, are you employed or not? And then it becomes a dichotomous variable. Opposed to categorical data, you have continuous data, which say this is a variable that can take any real value in the range of possible values. So if I was to look at income of an individual, it can lie between 0 and 1 million or more, whatever you want to consider. And this basically means that I can have an income of $0.1, $0.19, so including decimals, so any real value can be considered for income. Similarly, when you look at area of land that is owned by households, this is again considered in square meters, let's say. It could be, or acres or hectares, whatever your unit is. And again, this lies on a continuous scale and not, doesn't have these exclusive categories. Another example, which is more, let's say, discrete or more standard, is age. Age is a continuous variable, but is usually defined more discretely. So you have you're either 10 or you're 40 or you're 50, whatever ranges you define. And another similar example for this is years of schooling, for instance. Again, it is a finite number, but it still is a continuous variable that you generally discretely define. 2 characteristics that you can note here. Some of these cannot be less than 0. There are values that are continuous and can be less than 0. For example, we look at revenue. It's simply profit minus costs. And if your profits are not as large as your costs, your revenue can be less than 0 even, right? And these are sort of another continuous variable that is not bounded by 0 being the minimum value. And the second thing, of course, even age can be considered. Or you often hear kids say, I am 9 months old, which means this person, 1 year, 9 months old, which means this person is 1.75 years old. So again, here you can introduce non-discrete or more real non-integer values and make it more continuous. So these are sort of the differences between categorical and continuous data, and both of these require different types of statistics. So first, talking about categorical data, we have something called a univariate or something called univariate data, and now this is effectively just having is just taking one unit or one variable or one information from this individual and sort of aggregating it or tabulating it. And these are generally the forms that you see of how a single variable is described, and we will show examples of this later. And then there's bivariate data, which is to say that you are not just looking at one information of an individual, but 2 different sets of information or 2 different variables related to the same individual. And it's not just bivariate, it can be multivariate, which implies that you can have multiple sets of information. However, cross-tabulation is, so to say, disaggregation is sort of the methods that you use for bivariate or mostly trivariate data. So if you have 3 different sets of information that you're looking, again, the more complicated it gets, the harder it gets to summarize this information. And then for continuous data, we are looking at measures of central tendency. Again, there are 3. We will only focus on mean and median. And what is extremely critical for more advanced analysis and more inferential statistics is your measures of dispersion. And we will look at a few, or there are a few, and we will look at 2, which is specifically min-max or standard deviation. So again, we're coming back to our original setup, or the small example we gave in the previous slides, which was, let's say you are implementing a youth vocational training program in your TVET centers, right? And you have 4 TVET centers, or TVET being your technical and vocational education and training centers. And there is one, for your program, there is one overarching goal, which is now something a little more abstract, which is to say economically empower disadvantaged youth to engage in employment and livelihood strategies. Again, many words here that you cannot necessarily quantify. Is someone trying to speak? Okay. Good. So I assume there is no question there, but exactly. So you have your overarching goal, which is just economically empowering youth, right? Through a particular method, which is improving employment and improving their livelihood strategies. However, there are specific goals that always you would have in your program. In this case, we're looking at 4 specific goals and how we would sort of measure these 4 specific goals. First, we need to ensure that our program enrolls 1,000 young people to participate in the vocational training. A second goal is that we ensure that there is an even gender split, so 50-50 gender split across all participants, assuming 2 genders. Then there is a third specific goal that we're interested in, which is that there is a graduation rate of at least 90%. So of 1,000 individuals, 900 should have graduated the program. And through this program, what we eventually hope to observe is that your income has increased by about 800 units. So 6 months after training, we hope that individuals who have received the training are increasing their monthly income by 800 units. Okay. To be able to sort of reach these specific goals, now the question is and I hope some of you have already started thinking about it, is what information do we need? What data do we need to capture this? And some of this is, of course, evident. You need gender, so you need the gender of the participant. You need to understand how many did enroll. You need to understand how many graduated, and then eventually you need monthly income. And this is indeed provided to you. What is additionally provided is, of course, information at the TVET center level. So for each individual, you also know which TVET center they are enrolled at. And this allows us to do, actually, with just these 4 variables, we are able to do, or 5 actually, but we're able to do a lot with our, a lot of analysis already. So through these 4 specific goals, we eventually hope to measure whether or not our program was effective. Did it meet its targets? And for that, let's first look at the first specific goal, which is, did we manage to enroll 1,000 young people to participate in this vocational training program? As evaluation officers, or in your capacity as evaluation or supervising evaluation, you would then go to each of the TVET centers. Let's say in this case we have 4 TVET centers, and try to get the enrollment from all 4 of those. What it shows us, unfortunately, is that all of the centers, all 4 centers only had 462 participants. What this implies is the program has not reached its target. In fact, it has not even reached 50% of its target, 50% being at least 500 individuals, and here we are at 462 individuals. So the first specific goal has not been met. Let's move on to the second goal, and that now is, oh, yes, and before I move on, just very quickly, in case the program did not reach targets, now this is an interesting finding that you can explore either through quantitative or even possibly through qualitative analysis and investigation as to why. why was there such low enrollment? Was it possibly problems in the enrollment process, problems in the outreach, or just in general, what are the bottlenecks? And this is also something that you can explore through just this one variable. The second thing we're interested in is a 50-50% gender split. Now, again, gender is a categorical variable. One of the methods we talked about when talking about analyzing categorical data or dichotomous, in this case, data is to tabulate the information. So one table in this case will be representing for each TVET center, or just in total, what the distribution is between male and female. And what we find is, in total of the 462 participants, 232 are male and 230 are female, implying a almost even split of 50-50 between the two genders. It is therefore the case that we have met the second specific goal, that of the participants who enrolled, there is an even split within the two genders. But what you might have noticed already when looking at these numbers is that the split is not even across all TVET centers. So if the specific goal had been to ensure an equal gender split across the TVET centers even, or at the TVET center level, then we failed to achieve that goal. Specifically, if you look at cases such as this, where the female population is at 40 and male is nearly at 80, so it's nearly double enrollment from males versus female, this is definitely not an even split. Or here, where the differences are also, where there are 25 more females than males, which again represents 25% approximately of the overall participation. So again, this is where we first tabulate in general, and then if we again cross-tabulate across TVET centers, we get additional information. So this is now already the bivariate analysis that we are talking about, where we take gender on one aspect and divide that by TVET centers. So again, this is very simple, bivariate analysis. Now let's just look at an aggregation that is, or an analysis that is again tabulating a variable that, however, is described in percentages again, or proportions again. And this is the graduation rate. Now, our aim, if you remember, our specific goal was to have 90% of our population or our enrolled students graduate. What we find is that of the 462, so if you were just to look at the last row, of the 462 individuals, 422 managed to graduate. 40 dropped out during the training process. Therefore, our overall graduation rate is 91%. You can also aggregate it differently. For example, you take the percentages across, and you can also do it across each of the TVET centers to assess what the percentages are at each TVET center in terms of graduation. And if you look at the four centers, you will notice that there might be something that sticks out in this table. And that specifically is the values from a TVET Center 3, where you see that actually the dropout rate was much higher, so nearly 10% points more than the remaining centers at 16%, and thereby even the graduation rate is 10% lower, and lower than the 90%, which was the specific goal of the program. And now our understanding is, or our goal is to understand, why is TVET Center 3 doing perhaps or performing worse in terms of graduation compared to the other centers? And this is where we can cross-tabulate the same information and try to understand more or analyze more the single variable that we've been looking at, which is, for example, graduation. So To delve into this deeper analysis, we now look at, let's say, gender of the participants, another data point that we have for each observation. And what you would see is that if one was to look at the TVET Center 1, it's a pretty even graduation rate between males and females. This continues also for TVET Center 2 and TVET Center 4, which is slightly differentiated, but still similar. However, for TVET Center 3, we see actually that the graduation rate for males is 100%, but only 75% for females. So actually, while the overall graduation rate was 91%, if you disaggregate it by males and females, you would see that 96% of males, but only 87% of females are graduating. And most of this difference is actually driven by the TVET Center 3. So it's TVET Center 3 where the difference between male and female graduation rate is particularly stark. And so our goal as evaluators or program implementers even should be to understand why particularly is TVET Center 3 not doing well in terms of ensuring a female graduation rate as high as 90%. Or even as high as the male graduation rate that is observed. Right, so just to these three variables, or these 3 to 4 variables, we've established at least 3 of the goals, whether they were met, specific goals, whether they were met or not. Overall, we see that 2 of the 3 goals were met. However, when looking at TVET Center level, of course, there really none of the goals were met in terms of none of the specific goals were met, as you can see. However, now we go to the next or the last specific goal that we had looked at, which was whether or not the average monthly income of the graduates has increased by 800 units after completing the training. What is now income? As you remember, we already talked about income is a continuous variable, which means that we cannot use simple methods such as frequencies or proportions to describe it, which was the case previously. So frequency here being what is the number of participants that were in your program, or what is the enrollment number for your program. And proportions, for example, was the graduation rate. So what proportion of your enrolled group did graduate. But income cannot work that way and needs additional information or analysis method. And this is sort of what we are trying to understand through the measures of central tendency. So let's talk about what they are. In case you already know, this is going to be a recap, and in case not, then I hope you would learn something interesting from this as well. So the first measure of central tendency that we are interested in is the mean. What the mean effectively implies is that we take all the values that we have and sum them, add each value and then just simply divide it by the number of observations we had. To give you an example, we are looking at 9 individuals, male and females. Their average age, or their age, is basically given right on top of their heads or below their feet, as you can see here. So we have the age of each of these 9 individuals. If we were to now try to generate the mean or the average, as you often hear in reporting, the mean age for this individual, it would simply be summing up all the ages and then dividing it by the number of individuals, which here is 9. And what this gives us is a value of 33. And effectively what you can say from this is that on average, the individuals in our training program are 33 years old. And there's another method that is also sometimes used in reporting, and that is the median. What a median effectively is simply giving you a value that would evenly split or would split your data exactly in the middle. So it would mean at this value, 50% of your observations are below this value and 50% of your observations are above this value. Again, what this would mean, you sort all of your individuals by age, so 18, 21, 21, 26, and so on, all the way to 51, which is the oldest individual in your training program. And then we try to find that value at which we have a 50% or more or less even split between the two, within the group. What we see is at this for this individual at age 34, we are acquiring more or less a 50% split in our sample, and that is exactly, so to say, the middle value or the median value, to be more precise or more technical in our case. So the median age in our sample is 34. Quick remark on what the median implies. Because I talked about an even split at 50%, it also sort of implies that median belongs to the broader family of something called percentiles. What percentiles are simply values that split the data into different proportions, which could be, for example, 50%, which is the median. However, let's say you want to split the proportion, the data set into the bottom 10% versus the other remaining 90, or the top 10 versus the remaining bottom 90. And at this, you can also have, for example, P9, P10 or P90 as values. And P90 in this case would be the 10th percentile, which means that the bottom 10 is compared to the remaining, the top 90% of your population, or if you've done a split at 10 and 90. You can also divide it into 4 equal size instead of just 2 equal size groups, and these are called quartiles at P25, 50, and 75, and then last one, and through these 3 splits, we've made 4 different groups. Again, here the median exists between the second and the third group, so the second and third quartiles. And finally, you can continue dividing the sample as much as you like. Here we have an example of 10 equal size sets. These are called deciles. And if you were now to go all the way to the highest number of divisions, that is 100, it would be called centiles. And this is the concept of percentiles, with the middle value always being a median. So P50, or the second median, or like the quartile, second quartile, or the 5th decile is always defined as the median. And now coming back to income, which is our specific goal that we're still trying to measure, of 800 per individual. So now we've sort of seen what the measures of central tendency are. We have the mean and the median that we're looking at. So we have 462 participants, but let's say we just focus on a sample of 10 participants. Again, randomly, let's say, drawing 10 people from the sample, and we see that these are their incomes. So in 6 months, some are at 0, some are at 200, 700. These are the values that we see. And the sum for all of these is, okay, there's a typo there, it's 8,850. And what that means is basically we have the sum, so we have the numerator for our mean, and we know that there are 10 graduates. So we have the denominator for our mean. So we know exactly how to derive our mean simply by dividing 8,850, which is the total income in our sample, or sum of all monthly incomes for all 10 individuals, divided by 10 to arrive a mean of 885. What does this mean? The program has met its goal of, or the 4th specific goal of having an average monthly income of 800 for the graduates. However, looking at all of the individuals, would you be confident in saying, or would we as evaluators or as program implementers be confident in saying that the average income of the individuals here is 800? Again, if you look at this data, that is a little improbable for 2 reasons, and that is the outliers. So just to show you this figure, or what an outlier can mean. On average, you can have a depth of 3 feet, but exactly in the middle, there is a depth of 10 feet, and that's where you will drown. Or this is what will pull your entire analysis down. And the problem of outliers is also very, very critical in all analysis. The problem is that if you had one or two or some values that are lying extremely outside of the scope compared to the remaining values, or are very far away from the remaining values, it implies that your mean is sort of affected or biased by these very large or very small values that compared to the others. So now coming back to just a simple example of age again, where we were looking at the mean age of 33, right? What we saw is here, if we look at 33 as the mean age, 4 individuals are now below the mean age, and 6 individuals are above the mean age. Or, well, 5 to 6 individuals are at or above the mean age. So technically, we're at the center, or the mean is here a good measure of central tendency. Now imagine if one of the persons in the training program is 107 years old. It completely drives up our mean, and now we are looking at a mean of 40. What this implies is, if now I was to divide the sample on the basis of the average age of 40, all of these individuals, which is 6 individuals, are younger than 40, but only 3 are older than 40. Again, now we're moving away from the center, which is around here, and towards here as our mean value. So our mean has been moved upwards, or is biased upwards, due to the presence of one outlier, and therefore it's not very central and is problematic in terms of giving a, let's say, correct value for your overall sample, just because of one outlying value of 107. And therefore, these extreme values or outlying values are called outliers. And we will talk briefly about this also later. So what is the challenge that, that these outliers pose? And that is the fact that you can affect your mean and skew your data completely. And this is basically a concept that we also explained briefly in the appendix. But skewness is a measure to see how symmetrically you can see your individuals distributed, let's say on income or on age or whatever variable you're measuring. And here, for the age 34, in the first case, we saw that they were more or less equally distributed around, so equally further away from this measure of central tendency. However, in the second example, when we had an outlier, it was, you could see that the mean moved in a way that you had many more individuals on one side and fewer individuals on the other side. But more importantly, if you were to map how far this individual who is 107 years old is towards 40, your distribution or your dispersion of ages has become much further, or is much more skewed even. And this, for example, is something that one needs to consider when one is doing analysis as well. So the more asymmetric your data is, the worse the mean is as a measure of central tendency. So what variables can we think of that might be skewed in their distribution? And I hope you were thinking of some already. And if not, we can think of one in the coming examples. Before I move to that, I just want to briefly state that there is one key benefit of median, and that is it is robust to outliers, which means to say that if I was to look at the same group of individuals with 34, and the oldest individual being 51, or the oldest individual being 107, it doesn't matter, because we are simply taking a value which divides the sample by 50%, which means the mean is able to keep your sample more central and is more robust to outliers. However, what are the problems that we will see with the median? And this is basically something that we will also discuss within our session now. So for starters, coming to the mean, we already observed the mean. So the total income was 8,850 divided by 10 gives us a mean of 885. Again, this mean, if you place it into the order of things, shows us that nearly everyone is lying below the mean. Only one individual is lying above the mean. And if you were now to decide on what your median is, again, our median would take all the values and rank them by in an ascending order, and or descending, it doesn't matter. It's just usual to do it in ascending order. And what you see is that if all individuals are in the ascending order, there are two values that are lying exactly in the middle, and that is 300 and 350. And this gives us, and to acquire a mean for a two value, you just take the average. There are other ways to do it, but in our particular case, we are just taking the mean of the median, which is to say, summing 300 and 350, dividing it by 2 to get 325. And 325 is considered the median value for our sample. What it does is it has divided now the sample more or less evenly, wherein these individuals are below 325 and these individuals are above 325. Okay, so now we know that it's unbiased. The median is obviously unbiased compared to the mean when it comes to outliers. But is it enough to describe the data? And this is where we see the limits of using only measures of central tendency, only taking out averages, whether it be mean or a median. We need to consider the outliers, or as I already mentioned, the dispersion of your data across whichever variable you're interested in. And for this, we will talk about the measures of central measures of dispersion. In this case, the first measure that we're talking about is the minimum and maximum values. In your data, you can see that even though the mean is 885 or the median is 325, the mean, the minimum value is 0, whereas the maximum value is 6,000. And this already tells you a lot about how the data is distributed, so very widely distributed. Another measure, however, or the more standard measure that we observe in our reporting is variance or the standard deviation. And I'll just briefly going into what these two methods are. Variance is simply the overall variability on the data, to say it very shortly. To give you a more intuitive example, let's look at standard deviation. And it basically is just the measure of how far each of your value is from the mean on average. And what that means is not just how far each value is from the mean, but on average, what this deviation is from in your sample. What the standard deviation is simply a square root of your variance. So if you take the standard deviation and square it to the power of 2, or so, it would give you the variance. Or if you take the variance and do a square root of it, it will give you the standard deviation. So now the higher the variance is, or the standard deviation of your data is, the more dispersed the data is around your mean. And that is usually not a good thing. However, they are extremely important when you're doing your statistical testing. So these are concepts that we will also talk about in the next session and that we should be aware of. Okay, so let's look at how we can calculate a standard deviation. Now, again, coming back to our same 10 graduates, we are looking at a mean of 885. Again, what you see here, it divides the sample into 9 versus 1 individual, right? So not a great measure of central tendency. However, what's even worse is that our standard deviation is 1,810. Basically, what this tells us is that any of the graduate, if you take it, on average, their mean income is 1,810 units below or above the mean income, which is 885. Even if you haven't heard so much of statistics, this sounds like it's bad news. It should not be the case that you have such large standard deviation in your sample. And basically, while we know that the program has reached its objective, it's important that we look at the standard deviation to see the nuances in our data and our sample and how widely dispersed these incomes are. So while we will be very confidently saying, hey, look, we achieved our program goal, if someone was to ask you, show us your standard deviations, this would be bad news. And more importantly, if someone would have access to the data, you would obviously observe that this one value has driven up all of your meaning. So ideally, when you have the opportunity to present your data, or you're looking at your data, or you have someone doing the analysis for you and you're just looking at the report, it's important that you ask not only for the mean, which is telling you that you've met your program goal, but also at your standard deviation, which tells you that it's a very widely dispersed data set, or there are many observations that are lying outside of the usual distribution of income values. Always try to discuss the results to provide context and to explain and to nuance your analysis. However, it is known that often you just need to do a yes or no answer. So providing a mean like this would mean yes, you've met a target. However, as evaluators or as program implementers, it's important for us to understand where our dispersion in data might be causing a problem in our program goal calculation. Okay, so what can you do to deal with this skewed data? Again, skewness is just having a very widely dispersed data, particularly in one direction. Or how do you control for these outliers? And this basically would ensure that you have a more robust descriptive analysis. And to do this, we recommend two steps. First and foremost, try to visualize your data. If you visualize them, let's say all of your income values are around here, and this is where this is where you observe two outlying values. You have to see how you can cover them or process these or account for these outliers. In order to do so, we can do basically several things, but let's go back to our original example. So in our example, which I think I might have mentioned a couple of times, but also many of you might have hopefully observed, is that we have one clear outlier. How do you define or how do you measure something as an outlier? So there is no set definition for this. However, in econometrics or in statistics, you could define one outlier as something that is lying, a value that is lying beyond 2.5 times to 3 times the standard deviation. Again, if you remember, we can calculate a standard deviation as well. And in our previous example, it was 1,810 for a mean of 885. That means your outliers will be all values that are 4,000. So multiplying now this value by 2.5 standard deviations. So to acquire a 2.5 standard deviations value, we see it's 4,524. So this value is 2.5 times 1,810. And anything that is above this value or below this value would be considered an outlier. So starting with the case of below, so we simply have to subtract 4,524 from the mean of 885, and we see that below 2.5 standard deviations is already negative. Again, something we don't really expect with income. So in this case, we don't need an outlier analysis at the lower end of our data, or lower end here being 0, the few earlier income or low income values. However, it is critical for the higher end, because at the higher end, after adding 4,524 to 885, we see that our upper outliers would be values above 5,410. Obviously, this makes our graduate 9 an outlier, a clear outlier in our sample. So what are we going to do? we are going to see whether or not this is a real outlier. So depending on the origin, where this value comes from, we have to process this outlier differently, having identified it as an outlier. Okay, so let's talk about measurement error. We've already discussed it briefly or in last year, and Ellie very, very quickly touched upon it in this session, in the last session, when he said that you can have error in responses or you can have error in responses or error in recording, and this is related to data quality in general. So it could be that someone intentionally or unintentionally reports their income as 6,000 for whatever reason, and this is then an error in their reporting. Or when someone was writing down the income of this individual, instead of putting 2 zeros, they might have put 3 zeros. And this is an error in recording. And these are all just measurement errors. If you are confident as an evaluator or as someone who's looking at the data that this is obviously a measurement error, you can correct the data. So one measurement error can be something along the lines of someone being 200 years old. We don't know. We know that this is not possible. We know that we approximately know how long humans live. So someone being 200 years is not possible. And what you can do is correct this value if you have information on how to correct it, or you remove this observation. So now let's talk about how we deal with outliers, and there are three methods. First is so the first method is going back to the previous point about case deletion or removing this value of 6,000 from your sample. However, there are two other options available to you, and one of them is basically the method of imputation, and the second is vincerization. What is removal? I think is clear. You basically delete the entire value or observation from the sample, even if everything else was fine. This income is too absurd. We are removing this individual. But what is imputation? Now, imputation is something along the lines of you impute the value, or you take the 6,000 and you exchange it with another value. And how do you compute this value? It's basically taking another representative value. And often what you do with, let's say, about 10 individuals or more is to take the mean or the median value that you observe. So having done this, you would either replace the 6,000 with 885, which is the mean, or you would replace it by 325, which is the median. In practice, of course, the more you work with data, the more likely you are to use more sophisticated methods, such as even regression analysis, which we will talk about in the session tomorrow. The other option, or the third option, also in terms of what you can do with the data, is to vincerize the data. What does vincerization mean? Again, you take a minimum acceptable value. You say, look, the data cannot be so the value is the 90th percentile. Now, if you remember, the percentile was dividing the data into sections, into proportions. So the 90th percentile is dividing the data into 90% of the data being below and 10% of the data being above. And you say that everything that's above 10% is really just absurd values. These are not values that make sense. And all of these values will then be replaced by the value at the 90th percentile. So in the example, if you remember, the value at the 90th percentile is actually 6,000, is 700. So if you look at the data, you will just replace everything that is above 700 with just 700. So that value 6,000 will just be replaced by 700. Naturally, the differences now are a little higher. It can be at the 99th percentile, depending on how widely spread your data is, or the 95th percentile, which means that you replace the last 5% of the values only. Right, so The idea is through vincerization and imputation, you are able to keep the values, convert the outliers, so process them, whereas with removal, you're just deleting the entire observation and potentially lots of important information that you might require in addition to this, information on income, for instance. Okay, so in our case, as I said, we have 3 options. Try to use the mean and the median to visualize the data. Try to use your measures of standard deviation to understand what is happening with the dispersion of your data. And then if you observe or see outlying values, you need to process them, right? But it's important to note that there are still some values that are not necessarily measurement errors, but might be an actual value. Maybe there is an individual earning 6,000 out there, and then it's our job as evaluators to figure out why this is happening and to understand it. So watch out for your outliers. And so to end the presentation, to some extent, we just want to keep this idea in mind that some outliers will build actual information and should be kept in the data. And it's important to distinguish what is actually an extreme value versus what is an outlier. And this trade-off is something that you always have to deal with, or this measurement error, whether someone reported incorrectly or wrote it incorrectly, something one always has to deal with. Vincerization is a good method, imputation is a good method, or you just remove this observation to try to strike a balance between the very extreme values and an actual outlier. Remember again, the median as a measure of central tendency is much more robust to the outliers. But if you look at most reports, they are generally reporting means. And the reason for this is because in terms of a measure, it's generally the case that all measures, or very commonly used measures in statistics, have been devolved around means or rather than median. And this is why most descriptive statistics, so descriptions of your data, will focus on the mean income or the mean age, and not necessarily the median age or the median income. Right, and with that, we will hopefully go into just introduce, or I'm not even going to introduce it actually, I'm just going to quickly tell you that we will move into the session of inferential statistics and try to understand what kind of inferences can you draw from statistics using this measurement error as one of the example, and learn about characteristics of all program participants in practice using your data. Right, I will skip that part and just conclude the session. And we start with basically the next round, which is the interactive quiz. Okay, good. So there were a certain number of responses on what the correct example is, but in terms of impact evaluation, the question, does providing children with deworming pills improve school attendance, is a clear impact assessment. The reason why is we're establishing an effect as a cause of a program, which is effect is improving school attendance as a result of deworming pills being provided to children, as opposed to the other responses. Exactly. So here in the next question, we are asking, for a CIE, you need to have data on the program participants only. Is this now true or false, that you only need data on program participants for your method, for your counterfactual impact evaluation? So well done. 15 participants have correctly answered. It is indeed false, because the counterfactual impact evaluation relies on you having information on not just the participants, but also additionally on non-participants to create your counterfactual. Right, again, now the third question is looking for data collections for counterfactual impact evaluation methods. And the sample now here is referring to which of these 4 options. Is it all program participation as a sample? Is it those who were successfully surveyed? Is it all units of just the population? or is it the units that were from the sampling frame that was used for the collection of the data during the survey? So exactly, the units that are chosen from the sampling frame is always a sample. The rest is, for example, the population, the sampling frame itself, or basically the respondents.
So in this question, we are asking if we expect the program to have an impact of a given size. Does increasing the size of the sample for the CIE, the counterfactual impact evaluation study, will either increase your statistical precision or decrease your statistical precision, increase attrition or decrease measurement error?
Exactly. So in this case, we have 4 responses, but the correct response is actually it increases statistical precision. The more sample you have, the more you're representing your population, and the more likely you are to find that the information or the effect that you've derived is statistically more precise.
And to further stress, to decrease measurement error, you would have to look more at your questionnaire or improving your questionnaire to deal with that. So, so we just want to know what cross-tabulation is better suited for. We have 1 variable, more than 2 variables, or 2 variables.
Correct, actually, it is always more than 2 variables. It's already provided in the name. A cross-tabulation has, well, actually, cross-tabulation can also involve 2 variables, but in the example we showed, it was generally more than 2 variables. It's never 1 variable.
So we move to the next question. So we can measure causal impact with descriptive statistics, true or false?
Okay, so it's a little more evenly split than I would have liked. But it appears well, at least the majority understands that it's false. This was the entire last session where we saw that descriptive statistics are for aggregating, disaggregating, tabulation, but you're not measuring impact or causal impact using descriptive statistics.
Okay, so which of the following is not a statistical measure of central tendency? 1, we have the mean, we have the median, we have the middle, and we have the mode. Which of these is not a statistical measure of central tendency?
Great, yes, that is true. I repeated it enough times. So the middle is indeed not a measure of statistical tendency, central tendency.
So for continuous variables, the standard deviation measures. We have 1, how far each observation is from the mean on average. 2, how far each observation is from the median on average. And 3, how far the minimum and maximum values are from the mean on average.
Well done. Indeed, it is always the standard deviation from the mean, whereas from the median, we are always looking at the difference between the minimum and maximum values. So yes, indeed, it is the standard deviation from the mean.
So for the next question, we have for continuous variables, the median is calculated as. The first option is the square root of the variance, the square of the mean divided by the standard deviation, and then we have the value such that 50% of observations are below it and 50% are above it.
Yes, seems like everybody was listening in. So it is that the median divides your sample in such a way that 50% is below and 50% is above. Well done. Yes. Next question, please, Ali.
So for the next question, here we go. It is sufficient to report a measure of central tendency to describe data, true or false?
Exactly. So it's false to say that you can just report the measure of central tendency. We just saw how standard deviation is extremely critical to understanding your data or to nuance your data. So also try to report not just that, not just your mean, the number of observations there are in your sample, but also simultaneously the standard deviation associated with it. Thank you.
So in statistics, an outlier is a unit outside the sampling frame, a measurement error, a large positive value, or an extreme value, or a value very different from the others.
Yes, okay, so I'm not even going to explain it because the majority got it. A measurement error is incorrect reporting. Unit outside the sampling frame should not be taken into your sample at all. And it is also possible that an outlier is extremely large negative value as well, right? So whichever way the distribution moves.
So we move to our next question. So which of the following is usually considered as being robust to outliers? One, we have the median, we have the standard deviation, we have the minimum, and then we have the mean. Which of these is usually considered as being robust to outliers?
Okay, so what is robust to outliers is in terms of, okay, this maybe have been phrased differently in terms of a measure of central tendency, indeed the median. And the standard deviation is just a way to express how far you are from the mean. So, so maybe next time we'll phrase it as what measure of central tendency is robust to outliers. Last question.
In every analysis, all outliers must be removed from the data. We have true or false.
So there's a little participation here, but or fewer people responded to this, but yes, it is false that you must remove it all the time. You must remove it if you think it's a measurement error, but if it is actually telling you reliable and relevant information, then you need to investigate further to distinguish between a true extreme value versus a outlying incorrectly measured value. And with that, I think we are done with the quiz. Thank you, Ellie. And we can go into our break and hopefully see you everyone in an hour. Okay, good afternoon, everybody. Again, I hope you had a nice and refreshing break, because now we're going on to a slightly more complex topic, which I hope everybody is refreshed enough to listen. Again, it's all relatively intuitive, so please don't worry. It's going to be fine regardless. But again, I encourage you, if you have questions, if you see that you are unable to if you're unable to follow, please do interrupt me. Fortunately, there's also a break in the middle of the session for you to recap the slides that I may have brushed through too quickly, or that you need a bit more time on. Okay. Right, again, let's keep very intuitive or very critical questions for the end of the session, which would be end of the day session, which is at 3:35 Central European time. Yeah. Good. So just to provide a recap of what we talked about already, we were talking about descriptive statistics that are sort of compact but high-level summary of complex data. We were looking at attendance rates, we were looking at incomes, we were looking at gender distribution of your attendance and your, sorry, not attendance, enrollment and your even graduation, right? And through this, we were trying to look at specifically categorical data or at continuous data. These are the two data points that we were looking at. Specifically for categorical data, we were looking at frequencies, proportions, tabulations, or cross tabulations. And for continuous data, we even went into further to talk about measures of central tendency, specifically mean, which is just intuitively the average, but faces the problem of skewed data, and median, which is robust to outliers and just divides the population into 50%, right? And now we still did discuss something about outliers, right? We talked about these values or these certain observations that are lying very far from what you would observe the central values to be lying around. And they therefore bring about a wrong picture of your distribution of your data. It makes you think that everyone in your sample has 885 as a mean income, when actually most of the sample, so 90% of your sample, was below this value, and this one outlier of 6,000 completely skewed the data and gave you a wrong picture of the distribution, right? And to account for this, we talked about measures of dispersion, which are complementing you. So we talked about the minimum maximum, which is often used in the case of a median. And then we talked about variance and standard deviation. Now, these two were just associated with the mean and tell you how different, or average, how far your observations are from the mean. And the higher the standard deviation is, there's obviously more variability in the data, which means that your average difference to the mean for all data points is very high. And so these are sort of the key ingredients of inferential statistics. This is what we need to assess or be aware of when we do inferential statistics. So there are two questions we will ask ourselves. First, how confident can we be that the mean that we have in our sample actually represents the mean in the whole population? So again, going back to what Ellie mentioned once, but also was in your sessions last time, you have you're training 40,000 individuals. We can't interview or get data on all 40,000 individuals. So you go and interview 2,000 individuals. Are these 2,000 representative of the whole population of 40,000 that you are actually interested in? And the second thing that we are questioning ourselves is how confident can we be that the impact of that we're measuring of the program is actually the true impact? So is it something that we can consider as a correct impact for our sample? And these are the two things that, for example, statistical testing can help us with. So coming back again to our program of training youth for employment and income improvement enhancements, we are looking at 2,000 people who applied and 1,000 who were randomly selected. So we are going to our CIE method, which was a rigorous RCT. Again, we assume that all differences between the two groups are accounted for, or they are similar, and therefore any difference in the income or employment that we observe after the program is attributable to the program. And what do the data show us? So for 1,000 individuals who received training and 1,000 who did not receive training, the mean income is 1,200 for those who received training, but similar individuals who were not trained received an income of 1,050, which is 150 less. So would we be able to say that the program had an impact on income, and how confident are we that this is the true impact? This is actually what is true for the overall population. And so this is where we start going more into probability theory or more advanced statistics, right? And we have to start our testing with a hypothesis that we wish to test. Again, every sort of research question or every program should be guided by an evaluation question, right? So every time we start a program we should have a theory of change, we should have particular evaluation questions that we are interested in. And generally, your hypothesis is simply testing exactly your research question, or is derived from your research question. And therefore, the statistical testing would allow us to move past your assumptions and anecdotes to see whether our quantitative evidence is actually supporting our hypothesis, or is able to answer our evaluation question. So, to give you a brief overview of what we will cover and how we will cover it. So first and foremost, we will talk about what the hypotheses are that we will test within our statistical testing. Then we will talk about the sources of uncertainty. So there are two particular ones that we will talk about. So uncertainty because we're using samples instead of the entire population, and then errors that we make due to incorrect sampling. Then there is the steps of how statistical testing works. We talk briefly about one of the main tests that are used strategically in this most of the social sciences, and particularly for the type of data that we are used to. And then finally, how we can make a decision on this test. So again, this is all related to some basic statistics. So even if you don't have information on this, we try to make it very intuitive. But if there are questions, please feel free to interrupt and ask. Right. So let's talk about the hypothesis that I've mentioned a couple of times already. So the best place to start thinking for your statistical testing, as I said, is always think of a hypothesis. And now, what is a hypothesis? A hypothesis is basically a proposed explanation made as a starting point for a further investigation. Now, it sounds very complicated. Basically, we are trying to say that we are already proposing an explanation, and then we see whether or not this needs to be further investigation, or our hypothesis or our proposed explanation is already correct in the first place. And how do we know that our hypothesis is correct or not? It's because we test it, right? However, in statistical testing, at least in CIE or in counterfactual impact evaluation, we generally don't test it directly. We don't propose an explanation directly, or we hypothesize what it could be. We formulate something called the null hypothesis, which in statistics in CIE is noticed as HO. So H and not here, or null hypothesis. And then our idea is that we try to reject it to answer our research question. So the null hypothesis will always start with the assumption that there is no effect of the program. So there was no difference between our participants that got the program versus participants that did not get a program. And the goal of the analysis is to simply see if we can reject this null hypothesis and say, yes, there was an impact of the program or an effect of the program. So just to go back to our example, we were looking at higher incomes. Our initial hypothesis can be, if you have higher education, then the higher is your income. Right? So we were starting with the assumption that more education will lead to more income. However, the associated null hypothesis to this would be that the difference in income between those who completed primary education and those who did not is zero. So just effectively saying that if you have completed primary education, your income is zero compared to those who did not complete, or sorry, wait. Reformulate. The difference between if you having completed a primary education and someone who did not complete their primary education, the difference in income between these two is zero, and that is a null hypothesis. And we will set out to test whether this is true or actually there is a difference between those who completed their primary education or not. Okay, so starting with this definition that the difference is zero, we need to figure out two things through our statistical test. First, how confident are we when we reject the null hypothesis and we say that no, actually the difference is not zero. And this confidence is what we will also basically statistically measure or statistically define as something called statistical significance. This is the confidence through which we can say that the observed difference between those who completed primary education and those who did not complete primary education is reflecting the truth of the actual scenario. Right, so again, recapping very quickly, we set up our hypothesis indirectly, which is to say that there is no difference, and then we try to estimate the confidence with which we can say that yes, there is a difference, or that there is no difference. Let's now try to understand how we go about testing this hypothesis. So just testing whether our null hypothesis of difference in income between someone who completed their primary education and someone who did not. Okay, so again, we want to test our hypothesis for a population of interest, right? Now, a population, if you remember, is everybody who would be a person of interest and can be extremely large. This is everybody, let's say, in your sample. However, it's very rare to have information on the whole population and in your program. And even if you get information on everyone in your program, there are those who did not enter your program and who would still be relevant for your question, but are not part of your program and are therefore outside your program scope, but part of your population. And therefore, what we generally try to do is try to get a sample of your population, but ensure that the sample is representative. And in order to do so, we talked about this actually relatively extensively in year 2, but in order to do so, we take a subsample of the population of interest. You can, for quantitative data, it's generally the case that you rely on random sampling to select your sample from your population. Okay, now coming back to our hypothesis is that a person, the higher a person's education, the higher is their income. Now, this is not the null hypothesis, just the hypothesis that we are making. So if we are interested in testing income, basically the population of interest is everyone who is of working age, right? So those who should validly be earning an income. But it's, again, impossible to get it for the entire population. So we draw a representative sample and collect all the information, which is at least on education and age, through a survey from this representative sample. Now, just for simplicity, let's assume our population is very small. It's only 20 people. We know that most countries are not full of, most programs are not even of 20 people. Most countries are definitely exceeding 20 people. But for this example, we just move forward with 20 people. And then, in this case, we randomly pick 10 individuals and ask them if they completed primary school as our measure of education, and simultaneously ask them what their monthly income is. So everyone in green here represents our sample 1. This is what our sample 1 looks like. You have the names of these individuals, you have that they have completed primary schooling or not, and what their monthly income is. So now we test basically whether those who've completed primary school or not earn higher than those who have not completed primary schooling. So first and foremost, we need to separate the two groups, which is to separate those who've completed and those who have not completed primary schooling. And this is what it yields. We see that these 5 individuals completed primary school and these 5 individuals have not completed primary school. If one was to take the average of their monthly income, which is simply summing all of their incomes and dividing it by the number of individuals, which is 5, we get 1,280 units as the monthly income for those who completed primary schooling. Simultaneously, when we look at the group that did not complete primary schooling, we see that the actual average income they have is 990. So what we conclude through this, very simply, is that those who completed their primary schooling have a higher average monthly income than those who did not complete their primary schooling. But now we start questioning ourselves in asking whether or not this is sufficient evidence to reject our null hypothesis, or basically coming back to our hypothesis that higher educated individuals earn more. And this is where we talk about the uncertainty that we likely observe in statistics. So the first uncertainty is related to the difference we observe in our sample. And now we initially started off with a sample of 10 individuals, and we see that the difference between those who were educated versus those who were not educated in primary school is 290 units. This, however, as I said, is just our sample. It's just a subset of the population of 20 individuals that we have in our population, overall population. And what can happen is that the average that we calculate in our sample are not necessarily the true averages of the population. It could be that just because we have a particular specific sample that we have selected, this difference is exaggerated or even too low. And this is basically the chance that or the difference that might come into your averages because you're taking a sample versus asking the entire population. This source of uncertainty is basically called a sample or deriving, or the uncertainty that is derived from sampling versus asking the whole population. And as you know, this is something that rarely happens, that you have information on the whole population, and this is where inferential statistics will come in and help you. But first, I'll talk about the second source of uncertainty, which is type of sampling. Here we had in our initial sample selected 10 individuals randomly, and now let's draw another sample of individuals, and this is basically the sample 2, and compare the incomes of the sample 2. And what we see here, replacing the individuals, 4 individuals previously in sample 1 with these new individuals, has yielded a completed primary school monthly average of 1,070, and for those who did not complete their primary school, of 1,160. What does this mean? It shows us in this case that actually the individuals who completed primary schooling earn lower than those who did not complete primary schooling. And that basically is the issue that sampling or might introduce into your analysis. So it might be that based on sample 1, again, both randomly selected, you get a difference of 290, while by sample 3, you get a difference of minus 90 units, or that primary education is actually not yielding higher incomes. And basically, this is the second source of uncertainty that we're talking about, which is the choice of a sample that generates potentially a sampling error. So to talk about the 2 errors where inferential statistics can help us is, first, due to not having the whole population information and only relying on drawing conclusions for the whole population based on the information from a sample. And the second source of uncertainty is this uncertainty that comes from maybe sampling differently, which is called the sampling error. And as I said, this is what inferential statistics will try to help you resolve when testing your hypothesis. Okay. So talking about, all right, let me just keep track of when there is meant to be a break. Yes. So now talking about what exactly is the likely problem in the data and the sample that you're using. So we come back to our 10 individuals, and this is the data, monthly income data for all these 10 individuals, irrespective of their education. The first thing we do is try to derive a mean for this group, and we see that, okay, look, their average is 1,135. That is the average income for those in our sample. Again, we don't know whether this average is correct for the population as well. Is the population average in terms of income 1,135? Is it higher, maybe 1,300, or is it lower at 900 units? And so we need to figure out how close is this mean or sample mean of 1,135 to the true average income in the population. And this we can do with the help of a tool called confidence interval. Okay, so just showing one formula in your faces. It's basically on your screens. You see that you have confidence interval here. And it's basically something that relies on your sample mean, it relies on standard error, and relies on this value Z. And let me now slowly break down this formula for you to understand what confidence intervals basically imply. So just defining your confidence interval, it is basically able to calculate a lower bound and an upper bound for, let's say, income for your population. So what it will do is it will give you a population average lower bound and upper bound, and based on the information from your sample. So effectively, it is telling you the range within which the true population mean can fall. So the true average income for the sample will fall, and it gives you this with a certain level of confidence. Again, we're talking about confidence in terms of being able to estimate the true or having our sample mean fall within the true mean or the true mean of the population falling within or close to the sample mean of income. And so we have to estimate the confidence intervals with the help of two sources. We already know what the sample mean is. It's 1,135. Now we talk about standard error. Standard error is simply basically a measure of the discrepancy that derives from the mean calculated in the sample deviating from the mean of the whole population. It's sort of the sampling error or the second source of uncertainty that we were talking about. And how it's calculated is first using the standard deviation. So if you remember in our previous case, we had a standard, the average mean income was 885. And then we had this one value of 6,000, which gave us an extremely high standard deviation of 1,810. Remember? And the standard deviation is effectively simply your average distance of population from the mean of, average difference of each observation in your sample from the sample mean. And you take that standard deviation and simply divide it by the square root of the sample size. And this is your standard error or the sampling error that might have occurred in your data set. So again, our goal should always be to reduce our standard error. Yes? Does someone want to come in? Okay. All right. So so basically we have our confidence interval that is estimating where the true population mean lies based on where your sample is. That is then derived with the help of your standard error, which is simply the standard deviation divided by the square root of your sample size, and it's based on the sample mean. Now we come to the second. Oh, sorry. The next aspect that you see in your formula, which is the Z, and that effectively is the level of confidence. So again, as I mentioned that before, that you want to estimate these confidence intervals, but there are different levels at which you can estimate the confidence, right? So these are all now statistically derived values lying between 1 and 100. So of course, your level of confidence can be 100%. I'm 100% confident that my sample mean or that the sample mean or the population mean lies close to the sample mean, or you can be 95% confident or 90%. And so these are basically what we call as confidence levels or level of confidence with which we derive our range or our confidence intervals. So the range within which our population mean will lie. So the most common value that you would see very often in reports is that people often say at the 95% confidence level, we can say so and so. But also common in statistics or in other social sciences is the 90% and 99%. So also, for example, the tables we produce, very often we show show 3 levels of confidence, or at what level can we be confident about our results. So we generally report on 90, 95, and 99 for being able to tell you what kind of errors we are dealing with in our data. So I'll just, because now this was a lot of formulas and a lot of terminology which is new, I just try to give you a few statistical examples of each of these. So coming back to our data, we have a sample mean, as I said, of 1,135. I calculated the standard deviation on it. Don't worry, we will also, I think, look at an example of how standard deviation is calculated. But I calculated here already, so it's 226. We know that our sample is basically 10 individuals. And so how do you derive the standard error? It's simply the standard deviation divided by the square root of your sample size, which gives us a standard error of 71.5. Now, again, plugging it back to the formula, we want to estimate it for the 95% confidence interval. Again, relying on the particular test that we are interested in, the value or the confidence or the value at which the confidence level is 95 is 1.96. So plugging all of these values into this formula, we have 1135, we have 1.96 here, and then we have the standard error, which is 71.5. So we've calculated all 3 of these in order to estimate our confidence intervals, which is simply by generating Z times standard errors and first subtracting and then adding to the sample mean. So to give you an estimation of what the lower and upper bounds are, it's 994.8 and 1,275. What does that mean for our sample mean? It means that we have 95% confidence that the average monthly income of the whole population is between 995 and 1,275. Again, you can calculate this at the 90% confidence level or the 99% confidence level, whichever level you would prefer to have. Again, the higher your confidence level, the better. But there are problems associated with the changes in confidence level. So to show you what happens when we change the confidence level, again, coming back to our same example, I show you 3 different levels of confidence, right? So we want to be 90% confidence, no, we want to be 95% confidence, or we want to be 99% confidence. These associated Z values, again, there's lots of tables and resources for this online. You will see there are always exact Z values associated with this particular test that we're doing. And what that allows us to do is multiply the Z with the standard error, subtract and add it to the mean to get our lower and upper bounds. And what you can observe is that as the confidence level is increasing, our lower bound is becoming smaller and smaller. Similarly, our upper bound is becoming larger and larger. What this means, if I was to put my mean in the middle and then try to estimate the difference from this mean, at the 90% confidence level, my intervals will be closer to the mean. As I need to assess at a higher confidence level, or I want to be more confident in my results, I need to keep increasing this interval. So it deviates even further and further from our mean, giving us a lower likelihood of being wrong, but a higher likelihood of, but a very large confidence interval. What this means is that the more confident we want to be, the more imprecise or the wider our intervals are getting, and we have to accept. And so if we want to increase our precision, we have to accept a higher chance of being wrong. So if we want to be more precise, we have to go with 90% confidence level instead of 99%. And so now, again, we need to think of, okay, we need to estimate this error. We need to see how far or how likely it is that our sample mean is close to the population mean, or our population is similar to our sample. but we also need to ensure that we are not being too imprecise. And through this, we can think of ways to reduce our confidence intervals, or basically try to ensure that our chances of being wrong are reduced without affecting other factors too much. So how do we do that? And for this, I just go back to the same formula. So what we want to do is basically reduce the confidence intervals. Given that our sample mean is a given, what needs to happen is that whatever we add or subtract from the sample mean has to be smaller, which means this part of our formula has to be smaller to be able to subtract or add less to this and get smaller or tighter confidence intervals. The Z is a given, right? So for 90%, 95%, and 99% or whatever percentages you want, the Z values are assigned. So again, this is something that you cannot change, which means that our only sort of margin with which to improve our confidence is coming from the standard error. And again, I break down the standard error into two things, which is standard deviation, which was, again, how far you are from the mean. Each observation is on average from the mean, and divided by the square root of the sample size. What I hope some of you can see here, that there is one particular aspect here that you can manipulate in order to get tighter confidence intervals, and that is the sample size. So talking about the example, again, if we are looking, or if we are increasing the sample size, and just looking at the basic maths, what this would mean is this would increase and this overall would be decreased in general. So this value being decreased would thereby imply that what we are subtracting or adding to the sample mean is smaller. And therefore, our confidence intervals are becoming tighter without having, while ensuring, so we are getting more precise while ensuring that we are still maintaining a sample and not having to inquire every income from the entire population. All right, so for a given level of confidence, let's say what we can see here is that as the sample size increases, which is basically this component of your formula, the entire standard error, which is this component of your formula, will fall. So we want this standard error to reduce, which is what we will do by increasing the sample size. And through this, we are able to get more confident in our results or from our sample compared to the population. Right. So let's now look at how this works in reality. So we already did an example with 10 different individuals, and now we add 4 more individuals to make it a sample size of 14. So these 4 individuals are part of our sample now, and what this implies is now our sample mean has changed from 1135 to 1135.7. Our standard deviation is 223.1, and our sample size is 14. And again, we are coming now to the same formula. So you remember the confidence interval relies on the sample mean, which is the first part of our formula. And then you subtract and add the standard error, which is simply the standard deviation divided by the square root of the sample size, right? And that gives us a 95, oh, wait, I just realized. A 95% confidence interval of 1019 to 1252. Again, we can say with 95% confidence that our population mean, so the mean for the entire mean income for the entire population lies within this bandwidth. So let's compare the 2 examples that we have, right? So our sample mean was 1,135 in the previous case. Now it's increased by 0.7 units and it's become 1,135.7. Our standard deviation here is basically lower and our sample size has become higher. What this means, through this, our standard error has reduced double, first because of the decrease in the numerator and the decrease in the numerator and an increase in the denominator. And that means that due to the reduced standard error, our confidence intervals for the same 95% are now tighter. So you see this value of 995, which was further away from 1135, has now increased to 1109, which is closer to 1135.7. And similarly, on the upper end of our same interval, we see 1275, which was further away than 1252, which is closer to our mean here. And so we are now more precise, or well, not more precise, we are precise enough with 95%, but we have managed to shorten or tighten our confidence intervals. So just to recap in general, we have, through the additional 4 observations, increased our, or while keeping the same confidence intervals, reduced our confidence intervals, and basically are able to find a true average for the income of the population within a smaller bandwidth. Yes, and again, I'll recap before we go into the next break. First and foremost, we always have this uncertainty when it comes to drawing conclusion from a sample versus a population. And this is the main source of uncertainty, because we are sampling versus we are not having information on the entire sample. The second uncertainty that comes is that we have to calculate, that we have to sample, but sample might differ, or our sampling error might lead to different means when we sample differently. So one sample might give us a mean that is 1,135, another sample might give us a mean of 1,000 only. And how this affects us is that it could take our hypothesis either way. And what we showed you was one example in which those who had primary education had higher income compared to those who had no primary education. But in the second sample, also randomly selected, the value of the mean income was lower than for those who had completed primary education than those who had not. So again, the second error of sampling comes from the sampling error itself. And inferential statistics is able to account for both of these uncertainties through, first and foremost, your confidence intervals, which is basically talking about how far your population mean, or how likely it is that your population mean is close to your sample mean, and how uncertain can you be that your sampling error is accounted for. So how did we do this? The first uncertainty was captured by the confidence level. So we were talking about 3 confidence levels, 90, 95, and 99, which are, again, statistically, you can find the values also online where these values lie. In our particular case, for 95% confidence interval, we were looking at 1.96, right? And the second error that we are dealing with is just simply because errors come from sampling. Because we're randomly picking a population that we're assuming is representative, but another random pick might lead to a different population mean. And this is a standard error that we also capture through inferential statistics. Simply, it's a standard deviation, which is the average difference of your observation from the mean divided by the number of your observations or your sample. Good. So I repeated, I feel I mentioned the same words 2,000 times, but it's just to get the intuition correct, because now what we're going to do is also talk about it, how it works in practice. Right, so we are talking now about statistical testing in practice. We previously, or so far, we're looking at 2 types of uncertainties from sample. First, the fact that it's not your population, it's just a sample. And secondly, the sampling error. So how you sample might bring high or low error in your sample. In either cases, there are tools within statistical inferencing which help. So confidence intervals gives you an idea of with what confidence can you say that your sample mean is close to your population mean, for example, or where your population mean falls with respect to your sample mean. Again, looking at the example of income, right? And the second thing that we were looking at was your sampling error, which is estimated through the standard error, which is again simply the standard deviation divided by the number of observations. In one case for sure, which is to say your in order to reduce your your confidence intervals, you need to reduce your standard error. Again, this is something that you can do through the increase in your sample size, right? And so now we go through the steps of statistical testing, haven't gone through sort of the theory of how, what problems we face, what hypotheses we generate, and so on. So the steps are as follows. First, we generate or formulate our null hypothesis. Again, this is similar to the hypothesis that you derive from your evaluation question, but now you just phrase it so that the null hypothesis says that there is no effect or null effect, right? After that, you have to derive the statistic that you are interested in. So in this case, we are calculating our test statistic, the T-stat it's called, based from the student T, and I'll talk about this in a short while. This basically statistic is going to capture all your sampling error defined as the standard error in the previous example. Then, having derived our sampling error through our test statistic for our sample, we can do a second half, which is try to control for the confidence in our sample as opposed to the population. And again, for this, we have to define a critical value or a given level of confidence. Let's say, again, choose to stick with 95% confidence, which means that we have to find the value that is associated with that level of confidence. In the previous case, if you remember, it was Z, which was 1.96 for the 95% confidence interval related to actually the T-stat, which again, we will talk about. So having done all of this, formulated the hypothesis, derived our test statistic, and then decided on our confidence level, how do we test whether or not our two uncertainties are accounted for? And this basically is the entire premise of statistical inference. So you take the test statistic and you take your critical value. And if your test statistic value is lower than your critical value, again, 1.96 in the case of 95%, we do not reject the null hypothesis. We do not say, or we say that our null hypothesis cannot be rejected, which is to say, in our simple example, that primary educated people or individuals with primary school education do not earn differently from individuals who have no primary school education. The alternative rule is, however, and the one that we are interested in, is whether the test statistic value is greater than your critical value. And this basically is this allows us to reject the null hypothesis, which is to say that there is an effect or there is a difference of on income from the individual's education. It's important to know that these always are, let's say, positive values. So they're always positive. So if you cannot have a negative test statistic or a negative critical value. This is why we're always working in the realm of positive numbers here. So I tried to explain some of this here, but now actually in practice, and hopefully when you look at your reports and you're looking at CIE method-based report, you will see something called the p-value. And this basically is a very simplified statistical tool that that implies you don't have to do this calculation in your head as to whether the statistic or that you calculated is higher or lower than your critical value. All you have to do is look at the p-value. What is the p-value? the most intuitive way, technically not correct, but intuitive way of saying it is that it's a probability of being wrong when you reject the null hypothesis. So rejection of null hypothesis is what we are aiming for with the testing, and the p-value will tell you this is the probability of being wrong when you've rejected the null hypothesis. So let's talk about an example, or let's talk about the p-value first and then delve into an example. So p-value is a probability. It always lies between 0 and 1. So in some of the tables, you would see a p-value of 0.03. What that effectively means that it's a low probability. Alternatively, if you see a p-value of 0.97, that's an extremely high probability. And therefore, what this implies is with a value or p-value of 0.97, you can be rather certain that the probability of being wrong when you reject the null hypothesis is very low. Exactly. So, so now the second thing that there was another sort of very briefly mentioned word that I talked about, which was statistical significance. And this basically is the p-value is often compared to the significance level. And just to bring it all back for full circle, the significance level is basically very closely related to the confidence level that we discussed before. Now, confidence was just to say, how certain are we of our population mean being similar or being close to our sample mean, like, so those two being closely linked, or that our sample is not completely off from the population mean. Having derived our confidence level, we can derive the significance level by simply subtracting the confidence level from 100. So if we have a confidence level of 95%, which we said we are interested in, we want to be 95% confident, we will simply get a significance level of 5%. And then we are able to say either with 95% confidence or at the 5% significance level. Those are the two sort of terms that you would often see when you're talking about statistical testing or statistical inferencing, confidence or significance. And we will now sort of switch between these terms. So again, it's important if you have questions on this to just interrupt me and ask me, okay, why are we using this or why are we not using that, right? So now going back to the table on how I had presented it, right? So we had the 95% confidence level, which is the confidence level that you decide that you're interested in. This is the Z, or the critical value that we talked about before, which you compare your t-statistic to, right? And this is already defined through a normal distribution, a table that we already have, like that you can find online anywhere. So for every confidence level, you would find a given Z value. For the 95% confidence interval, the Z value was 1.96. And through that, we derived our upper and lower bounds of the confidence interval. So the last thing, the last column that I also discussed is the chance of being wrong. And that simply is your significance level. So it's basically 100 minus 95, which is 5% significance level. And this is, so to say, one table that tells you more or less exactly how statistical inferencing works, with the exception of course, now the p-value. And this is and in the next slide, we basically we will basically look at how p-values can be interpreted. So now we've switched from confidence level to significance level. So again, you remember that the higher the significance level, the lower the confidence level. Again, we must always aim for more confidence and thereby less significance. So at the significant level of 1%, we can be 99% confident, right? How and what you're doing with the p-value, instead of now taking the test statistic, comparing it to the Z score, you simply look at the p-value and take this value, which lies between 0 and 1, which is the probability, multiply it by 100. So if you multiply 0.1 by 100, you simply get 10%. If you multiply 0.09, you get 9%. And so basically, all you have to do to interpret the p-value, is to multiply this by 100, and then you can see what is the significance level with which you can say that we are this % wrong at rejecting the null hypothesis. So for a p-value of 0.09, we are having an at most 9% chance of being wrong if we reject the null hypothesis, which means that we are 91% confident that we reject our null hypothesis, right? A null hypothesis is, again, do individuals with primary education have higher incomes? So any value that is 0.1 is referring to 10%, and lower will mean that at the 10% significance level, we are observing a rejection of the null hypothesis. And so we continue, or we can look at smaller and smaller values until we reach something like 0.98, and 0.98 is basically such a strong confidence level wherein you're saying, look, we are at most having a 0.98 chance of being wrong if we reject the null hypothesis. In this case, I'm just looking at 1%, and what I see is there's at most a 1% chance of being wrong if we reject the null hypothesis, and so we are 99% confident in our results. So I tried to give you all three. You can just stick to one of them. If you use one of them, it's already enough. Let's say you, so if you want to stick with confidence, you can take the value 0.1. You say we reject a null hypothesis with 90% confidence. You do not, this interpretation is something a little more easier for you to understand, or is put in there for you to understand. But as you read a report, you will either see 90% confidence level or 10% significance level, and you can choose which one you prefer to work with. So just in terms of how it works in practice, to quickly go through it, our null hypothesis is the difference in income for those who completed primary education and those who did not is 0. So we run so given the data we have on income, we simply compare the mean between the two tests through a statistical test called the student's t-test. Again, some of this more detail is provided in the appendix. To our t-test, we calculate the p-value, and using our p-value, we see whether we can reject our null hypothesis or not. And coming to an example here, again, the 5 individuals that completed primary school education and did not complete primary school education. Our hypothesis was the higher a person's education, the higher their income will be. What do we do here now? We check or we run our sample data, and we calculate our t-test, right? And from the t-test, we find a p-value of 0.032. What do we have to do? Multiply this by 100, which means we come to a value of 3.2. What do we conclude on this test? Again, let's now first look at all, or I'll give you all 3 definitions, and you can decide the ones you work with. In other words, we have a 3.2% chance that the difference between the groups is due to random chance and does not exist in the population. We didn't talk about this in the previous cases, but this is effectively what a p-test will show, a p-value will show you. It's that there's a 3.2% chance that the difference does not exist in the population, right? Or you're wrong in rejecting a null hypothesis. Alternatively, what you would often find in statistical texts is we can say with at least 95% confidence, even actually all the way up to 97% confidence, that people who complete primary school have a higher income in the population. And then finally, we can say in terms of statistical significance that the difference in average income between the two groups is statistically significant at the 5% significance level. Again, I just use the 95% threshold here. You can use different thresholds, but in the literature, you generally stick to the 3, 90, 99, and 95. And you compare your p-value, which is 3.2, is less than 95, and so you're confident, right? So you're 3.2%, there's a 3.2% chance that you're wrong, but you're 95% confidence, and or your statistically significant results at 5% significance. Right, just again, final recap on what we talked about. Statistical testing will exploit information from the sample to draw inferences about the population. We always define our hypothesis and generally the associated null hypothesis, which is not a simplistic, wherein we try to reject our null hypothesis through our testing. We define our confidence level, or alternatively 100 minus confidence level, the significance level, right? And then we calculate the p-value to conclude how confident we are with the results. So the smaller the p-value, the better it is, right? The more confident we are in rejecting the null hypothesis, which is basically the entire premise of statistical testing. Some notes to remember. We just showed you one test, or I briefly ran over one test, which was the student t-test, right? Which is very commonly used in the data. But for different type of data, you have different types of tests. There is the chi-square, there is f-test, etc., which you can also use, and you might have even heard of. And the similar logic is basically applying to all other tests. You have one critical value and you calculate your test value, and then you compare your test value to your critical value. Another thing which we talked about was the increase in sample size and how it obviously leads to a reduction in uncertainty and improves your confidence interval. A similar intuition holds for the t-test. Basically, the larger your sample size, you're getting more information of your population, right? So you're just reducing your uncertainty that arrives from samples. And that's basically meaning smaller standard errors, improved t-test or t-value. And larger sample size, of course, also reduces uncertainty due to sampling. Okay. I will skip this part on beyond statistical testing, because now we're actually already over and we should be going very quickly into the guided example of walking through a t-test. But just remember, this statistical testing that we're showing you is just a formula. You know, it completely depends on your analysis and your context. And you need to figure out whether your data is correct, whether you're contextualizing your findings well. Do you need to look at differences across gender? Do you need to look at differences across primary versus secondary schooling? All of these are important contextualization that you need to think about when you set up your null hypothesis, right? And again, try to learn or try to understand the implicit difference between a population and sample, and for that you rely on statistical inferencing through these tests, and one of the tests which I showed you. Yes. The last part, of course, always reverting back to what we talked about in year one. Just because you're statistically able to infer something does not mean that it's a result of the program. So here we were always testing whether primary education led to higher incomes. This does not mean that if you get a primary education, it would mean you have higher income. This is something that you can only establish if you can establish causality with a counterfactual, right? So this is the reliance on a CIE method. And so within CIE methods, we would run the same test, but be sure that there's effect, or this rejection of the null hypothesis is a result of the program and not because of other factors. Good. So Moving on to the next example, or just the example, basically, I'll stop sharing my screen here, and I'll share the test value. And I'll try to, again, keep an eye out on any questions that you have on the side. But yeah, so looking at this is basically actual survey data that we have derived for one of the projects that we are doing or we are evaluating for the EUTF actually. So this is real data, and what we have here is the income level based on primary education. And what you see here in the first column is individuals and their primary and their income for having only completed primary education, and then you have secondary education and the income level of a similar, how many individuals is it? 15 individuals who have completed secondary school education. And now we will try to quickly derive each of the statistics that I've briefly talked about. Again, I hope that I believe you should have received the same sheet from Carolyn, so you can do it simultaneously as I'm showing you. And I'm sure many of you have already done this. So, so part of this sheet will be easy. And what we do is first calculate the average income for those who have primary education. Again, this is just the mean that we are calculating, right? So go to this box FX here, click on it. And what you're trying to derive is the average, right? Click on average and then go. Oh, wait, sorry. Cancel. Sorry. Click on average again. Apologies. Click on average, and then it would ask you for the function of your argument. So now this basically is just the set of individuals that you want to calculate the average for. In our case, our average is going to be A4 to A18. Just drag down the value A4 to A18, and with that, you get the average income for everyone who has completed primary education in your sample. I'll repeat it again now for everyone who has secondary education. Again, click on this formula, select average, and then you know that you want to select all the individuals who have secondary education in your sample. So you click and you select all of them. After clicking OK, you see that the individuals who have completed primary education have an average income of 162.8, which is, sorry, not 100, so it's 162,844 units, and I believe this data is actually from Uganda, so shillings. And for secondary education, actually, you have lower average income of 152.340 shillings, Ugandan shillings. Then we try to calculate the standard deviation. Again, there's a formula for this. Sorry, I always keep doing it the way I do it, but here we're interested in calculating the standard deviation. This is now the standard deviation. Simply click on this, double click on this, and then do the same for those who have primary education. So we're interested in calculating the standard deviation for these guys. And we click on OK. This is standard deviation, which is 131,088 shillings. Again, pretty high number for your standard deviation. But again, one must remember or keep in mind that income is one of those variables that has very high deviation in the first place. Coming now again to the standard deviation now, but for your secondary school education educated individuals, and that is here. Again, click on OK, and now we have a lower standard deviation here of 112,866 shillings. So through this, you don't even need to know the formulas that I kept throwing at you. All you need to do is understand how you can calculate this. Use the function formula here to be able to generate this. Now we try to generate the difference in mean. Here, instead of relying on formulas, we will do something simple, which is just write down the formula, which is equal to. What is the difference in mean? It's basically the difference between the group 1 subtracting group 2 from it, right? So we are interested in getting our differences here and establishing what they are. Why do we need this difference in means? It's because for the comparison of means, we need to rely on this difference in means. Okay, good. So having done that, actually remember that it should be G5 minus G4. So it actually has to be negative because we're trying to compare these minus these, right? So this is a minus value, and now we calculate the p-value. Again, for this, it's something that I've already talked about. We calculate the p-value for the t-test only. There are also other p-values you can calculate in Excel, but in this case, we're focusing on the t-value, right? So again, you click on your cell where you're interested in calculating it, click on function, and then you can also type here directly so that it shows you what options are available for you. So as I said here, you have chi-square test, you have the F-test, these are the other tests I was talking about, but we are only interested in the t-test. Having double-clicked on it, you now need to enter all of this information. Array 1 is basically simply trying to derive the average income for your primary education. So we now recalculate it and put it in here. Oh, all right. And we have to put all values in your array. So this was my fault. Here, starting all over again. T-test. Your first array is these guys. Your second array is now the second set of individuals in your sample, which is your individuals who have a secondary school education. Here, again, now you enter the second set of individuals. If you remember, you need this information just so that Stata knows and is able to calculate the average income and the standard deviation for both of them. Now we come to a sort of complicated aspect, which we've not talked about, which is the tails. Generally, the t-test can be calculated as a one-tailed test or a two-tailed test. Again, some of this information is provided already in the slides, but we will also share additional slides on what this means. For our test, we are testing whether with two tails, or we assume that the mean is we can calculate it for both sides of the distribution. So here, please just write 2. And for type, we write 3 here. Now, what type is just the type, the kind of t-test that we're interested in. There's a paired t-test, there's a 2-sample equal variance or homoscedastic t-set, and 2-sample unequal variance. So these are the 3 options, and we specifically put 3, which, if you remember, variance is a measure of dispersion, and we are assuming here that our sample has, or the 2 samples we are comparing have unequal variance. When in doubt, I always go for 3. If you think your sample is not very different from each other, the 2 samples that you're looking at, then you can go for 2, but generally the idea is that you go for 3. Having done this, what you see here is that we have a p-value of 0.816. And through this, what can we conclude? Basically, that we are unable to reject our null hypothesis. Remember, we want the p-value to be as low as possible in the example we were looking at, it was 0.032. So we multiplied this by 100. Now, if I was to show you an example, you would simply take this value, multiply this by 100. Oh, multiply, sorry. And this would, oh, what am I doing? G10, no, it's H10. Okay, I'm obviously not very capable with with Excel. I apologize for that. And it's this guy, G11. And what you see is that your p-value tells us that it's 81.57, where our 95%, we are far, far, far above your 95% confidence level, or the 5% significant level that we were always comparing again. We are at 81.58 versus a value which was initially 3.2. So again, we cannot reject our null hypothesis here. And a null hypothesis is basically testing whether the average income between these two sets of individuals is different. One having primary education, one having secondary education. So our null hypothesis is not rejected. We cannot say that having a primary education or having as opposed to a secondary education will yield that there are differences in income between the two. I hope that the example was a little clear in understanding what the difference is. I hope some of you were also able to follow how the test ran or how we conducted this test. And if yes, then there's always an example tool which I encourage you to also look through and try to do on your own. Basically, these are the hypotheses that I have posited here. So it's related to various variables: age, gender, income. Try to calculate the averages here. Try to calculate the standard deviation. Try to remember what kind of variables we have, categorical, continuous, and see what all you can work with. There are outliers, there are no outliers. These are the kind of things that are sort of highlighted here, and I encourage you to please look at it in your free time or after the training is over today and potentially before the training on regression analysis tomorrow.
Atika, we have a little request in the chat. Could you kindly repeat the t-test calculation?
Yes, I can do that. Yes. So I hope you can see my screen. Go to so I'll just delete this here for now. Okay, so we want to calculate the p-test. It could be in any cell. I'm just doing it in this cell, of course, because, wait, sorry. Do you want the t-test or the p-value for the t-test? I didn't get that.
Let me check.
I think it's the t-test.
Yeah.
The t-test.
The t-test. Okay. Yes. So let's look at that again. Here, click on the cell, which is fine. This is now the t-test that, obviously it came up first for me. I hope you clicked on the function formula. In case it's not coming up first for you, please type t-test and it will give you whatever options are available here, right? So you can see several options come up. The one that we are most interested in, the first one, click on the t-test, double click, sorry. Then you have to present the two arrays. So this is the two samples that you are comparing. Array 1 is those who only have primary education. Array 2 is basically the set of individuals who only have secondary education. So just scroll through all those values and select and add them. The tails are basically specifying whether we are looking at a one-tail distribution or a two-tail distribution. To explain this a little bit, in case that is what is causing the confusion, generally your tails are, there are two types of tests. There's a two-tail student t-test and there's a one-tail student t-test. And always the idea is that a two-tail t, which is generally what you observe in your sample, the two-tail t-test is simply telling you whether or not you have a one-sided test. If you want, so give you an example of a one-sided t-test, you would say that the income of, or your null hypothesis for a one-tail t-test would be that the income of people having primary education is higher than those who have no primary education. So you always specify a direction, and that's the one-sided test. In our test, we did not specify a direction. We said it could be higher, it could be lower. We just care about the difference. And this is why it's a two-tail test. And that's why I put a 2 here, to provide just a bit of the intuition. Talking about the type again is now the kind of test that you're pairing with, or a type kind of a t-test you're running. In this case, there are 3 options. There is a paired t-test. There is the 2-sample equal variance, 2-sample unequal variance. Now, again, we have 2 samples, so the paired t-test is irrelevant here. What we are interested in, however, is the variance in our sample. When you're uncertain of whether or not, and the variance again is, if you briefly remember, is simply the square of your standard, or it's a lot more complicated actually, but it's simply the square of your standard error. And if that, I mean, and basically it's just saying how is the variance in your sample is the square of your standard deviation. And it's basically just taking your entire distribution and assuming that these 2 samples have a difference in variance, or they are dispersed differently from the mean. That's all the variance is trying to show you. And usually what we observe in real life is that there is indeed a large difference between the 2 samples. So this is why this is a difference variance category that we're taking. So we're relying on the 2 samples, and unequal variance, which is to say that both have a different variance of your observations from the mean. And that's why we put 3 here and then click on OK. And with that, we get a value of 0.816, which is basically 81.56, a very high p-value. Therefore, we cannot reject our null hypothesis. I hope that was now clear on the steps. Okay. If nothing else comes up, we still have, fortunately, now the Q&A session. We've eaten actually into most of it, but I'm happy for more questions. Now is the time that you can ask me all your questions related to whatever we talked about the training, throughout the training, through all the sessions. Ellie is also around, so you can also ask him a bit more about data collection, data cleaning, whatever questions you have right now, before I eventually hand over to Ellie again, who will have a short feedback round from your side. Again, we're happy to receive feedback and happy to see what you are more interested in, less interested in, and how we could provide a better and more inclusive training. So please do stay and give us that feedback. But for now, let's just talk about questions you might have. Okay. So no questions, I see. In that case, what we could do is we can simply have we can just push forward our closing of the session. And I'm happy to hand over to Ellie. for the closing of the day today.
Maybe just one question. Sorry.
Yes, please go ahead.
So the findings in this example that you have given us, is this expected? For example, if you conduct a research and you expect that people who have finished secondary school would earn higher, and then you have a result like this, does this say the data is wrong or your hypothesis is actually wrong? Thank you.
It's not an expected result. Generally, we would expect higher education. Well, actually, let me qualify that statement already. We would expect higher education to bring higher gains in income. However, depending on the country, it can be that whether you have primary education or secondary education, it does not matter. It's only that if you are beyond, let's say, if you've completed university education, that's the only time when you observe gains in income. So it's not necessarily a completely unexpected result, because we were just comparing secondary education to primary education. So it's not a very out of the world result, but for the hypothesis that more education should give you more gains in income, this is an unexpected result. Yes, the hypothesis can be anything, right? It could be, that the older you are, the more likely you are to be married, or what, you can have, or there's a higher, older individuals are more likely to be married, or the older you are, the higher your income is. These are all hypotheses you can make and test. So there's no, let's say, wrong hypothesis. Thank you for that question. Okay. Then if there are no other questions, again, there's a question and answer round tomorrow. I can understand that a lot was discussed, so it might be too much right now, but feel free to talk about it tomorrow as well, during the question and answer round. And I'll hand off to Ellie, who can then just have a short feedback round with you.
Thank you very much, Attica. So this is just a very short feedback session. As Attica mentioned, we would like to know, would like to get feedback from you as to which parts of the presentations you probably liked and what you probably didn't like. So please feel free to give us honest feedback. We just want to use this to improve on the further trainings that we will be having.
Yeah, thanks a lot, Ellie. Thanks a lot, Attica, for the first day of our training for this year. I hope you enjoyed it, and yeah, you could learn a lot from the presentations. We will share the presentation on all the material with you after the second day. And tomorrow we will start like today. We will start at 10. And yeah, we will then have a very short welcome session, but then we will start with another technical session, and we'll have on the day as well some breakout sessions where you then actively be involved in the training and have time for questions and also for new thematics. So yeah, I thank you all for participating, and I'm looking forward to tomorrow's seminar. And that's all from my side. I wish you a good rest of the day, and I see it's perfect timing. We have it 4 p.m. in the afternoon, exactly how the agenda says. And yeah, looking forward for tomorrow, and bye-bye.